In your lifetime, a human being will stand on another planet, and it starts with a tiny red ember that doesn't twinkle. It just sits there watching. That's Mars, 40 million kilometers away on a good day, 400 million on a bad one. We've sent machines there, photographed its storms, and yet we still haven't sent a person. So how long does it really take to reach that world? If you love this kind of content, please subscribe to the channel. Now let's get started. The first thing you need to understand is that space is not like driving across a country or even flying across an ocean. On Earth, distance is distance. You get in a car, you drive 300 kilometers, you arrive. Simple. Space laughs at that kind of thinking. The distance between Earth and Mars is not a fixed number. That's the first twist. These two planets are not sitting still next to each other like two parked cars. They are both moving, orbiting the Sun at different speeds, on different paths, constantly changing their position relative to each other. So asking how far is Mars is actually a lot like asking how far is your friend, when your friend is constantly jogging around a track, and you're jogging on a different, slightly larger track at a different pace. Sometimes you're on the same side of the track, close together. Sometimes you're on opposite sides, as far apart as you can get. When Earth and Mars are at their closest, a moment astronomers call opposition, the distance can shrink to about 54.6 million kilometers. That was roughly the situation back in 2003, when Mars made its closest approach to Earth in nearly 60,000 years. People around the world stepped outside with binoculars and telescopes just to catch a glimpse. It was the brightest Mars had appeared in recorded human history. But when Earth and Mars are on opposite sides of the Sun, that distance balloons to over 400 million kilometers. 400 million. Let that settle in for a moment. So already, before we've even talked about rockets or fuel or trajectories, you can see that the answer to how long does it take to get to Mars depends entirely on when you leave. Timing is everything. Now here's where it gets really interesting, and where the physics of space travel starts to feel almost like a puzzle you want to solve yourself. You might think, okay, if I want to get to Mars as fast as possible, I should just point my rocket straight at Mars and go full throttle, right? Burn as much fuel as possible, aim directly at the red dot, and push. That's the intuitive answer. It's also almost completely wrong. Space travel doesn't work like driving a car. In space, you're not fighting friction or road resistance. You're working with gravity, the invisible, elegant force that governs everything from the orbit of electrons around atoms to the spiral arms of entire galaxies. And gravity is not your enemy in space. When you understand it, it becomes your most powerful ally. The smartest way to travel from Earth to Mars isn't a straight line, it's a curve, a graceful arc called a Hohmann Transfer Orbit. Picture throwing a ball in a way that lets it coast along the natural pull of the Sun's gravity, curving outward from Earth's orbit until it meets Mars's orbit, exactly where Mars will be when you arrive. You're not chasing Mars, you're predicting where it will be and letting gravity do most of the work to carry you there. This orbit was first worked out mathematically by a German engineer named Walter Hohmann back in 1925. He figured out that this curved path requires the least amount of fuel of any route between two planets. And for spacecraft, fuel is life. Fuel is everything. The less fuel you burn getting there, the more you can carry for landing, for life support, for the return trip. So the Hohmann Transfer Orbit became the gold standard for interplanetary travel. And using this method, the trip from Earth to Mars takes, depending on the exact alignment of the planets, somewhere between 6 and 9 months. Most missions aim for closer to 7 months. 7 months. That's not a weekend trip. That's not even a long vacation. That is a profound, extended journey through the deep void of space. And it's worth pausing here to really feel what that means. 7 months in a spacecraft, no fresh air. No open sky, no feeling of wind on your skin. You wake up every single day inside a metal capsule, hurtling through the emptiness between worlds. Earth shrinks behind you from a vibrant blue marble to a small pale dot, then smaller, then it becomes just another point of light among billions. The astronauts who will one day make this trip will be farther from home than any human being has ever been. The Apollo astronauts who walked on the moon were about 384,000 kilometers from Earth. A Mars-bound crew would be tens of millions of kilometers away, far enough that a radio signal traveling at the speed of light, the fastest anything in the universe can move, would take anywhere from 3 to 22 minutes just to reach home. And the same amount of time for any response to come back. No real-time conversations with your family. No instant contact with mission control. If something goes wrong, you solve it yourself. That psychological weight is something scientists and space agencies are studying intensely right now. Because the technology to get to Mars, we're closing in on it. But the human mind and body, that's another challenge entirely, and one we'll dive deep into in just a moment. If this topic has you fired up about the challenges of deep space travel, you are going to want to watch my video exploring why interstellar travel is a brutal one-way trip on the card above. It takes everything we're discussing today and scales it up to a level that will genuinely make your jaw drop. The physics are real, the consequences are staggering, and it completely reframes what it means to explore the cosmos. The link is in the description and pinned on the comments, so we've established that using the most fuel-efficient path, you're looking at roughly 7 months of travel. But here's something that doesn't always make it into the headlines. The spacecraft currently traveling to Mars don't go in a straight line, and they don't travel at a constant speed. Let's look at some real numbers from real missions to give you a sense of what this actually looks like in practice. The Mars Odyssey spacecraft, launched in April of 2001, took about 200 days to reach Mars. That's roughly 6.5 months. It traveled approximately 460 million kilometers, not because Mars was that far away in a straight line, but because of the curved trajectory it followed. The Mars Reconnaissance Orbiter launched in August of 2005 and arrived in March of 2006, about 7 months later. The Curiosity rover launched in late November of 2011 and touched down in August of 2012 after a journey of about 253 days. It covered roughly 560 million kilometers along its curved path, and Perseverance, NASA's most recent Mars rover, launched in late July of 2020 and landed in February of 2021, 203 days, about 6.5 months. These are real spacecraft, real journeys, real numbers. And every single one of them launched during a specific window when Earth and Mars were in the right alignment for a Hohmann-style transfer. Miss that window, and you either wait roughly 26 months for the next one, or you burn enormous amounts of extra fuel to compensate. 26 months. That's how long it takes for Earth and Mars to realign in a favorable position again. So if you're planning a crewed mission to Mars, you don't just decide to go. You wait for the universe to give you the green light. That window, that narrow slice of time when the geometry of the solar system lines up in your favor, is one of the most important concepts in all of interplanetary mission planning. And it reveals something profound about our relationship with the cosmos. We are not in control of the universe. We are guests in it. And traveling through it means learning to work with its rules rather than against them. There's something humbling and beautiful about that. The same gravitational dance that governs when we can launch a spacecraft to Mars also governs the tides on Earth, the formation of galaxies, the orbit of every moon around every planet in the solar system. We are all part of the same vast interconnected system, particles in a universe that has been playing this gravitational symphony for nearly 14 billion years. And right now, in this moment, you and I are small but conscious pieces of that system, curious enough to ask questions about the stars, and determined enough to build machines that can reach them. We've covered a lot of ground in this first section, and we're just getting started. You now understand why the distance to Mars is not fixed, what a Hohmann Transfer Orbit is, and why it's the preferred path, how long real missions have taken, and just a hint of what the human experience of that journey would feel like. But here's what's coming next, and I promise you, this is where things get genuinely jaw-dropping. What if 7 months is too slow? What if we need to cut that travel time down dramatically, not just for convenience, but for survival? Because the longer astronauts spend in deep space, the more their bodies are exposed to something that doesn't care about your training, your fitness level, or your courage: cosmic radiation. And the solutions that scientists are actively working on right now, nuclear propulsion, solar sails, and technologies that sound like they came straight from a science fiction film, are more real and more imminent than most people realize. That's exactly where we're going now. So we left off with a question hanging in the air like a planet waiting to be discovered. 7 months. That's the standard answer. That's what the textbooks say. That's what mission planners use. That's what the rovers we've already sent to Mars have demonstrated is achievable. But here's the problem, and it's a big one. 7 months in deep space might be enough to kill you before you ever land. Not because the rocket fails, not because of a meteor strike or a mechanical malfunction, but because of something you can't see, can't feel, and can't escape. Something that has been quietly bathing our solar system in danger since long before our planet even formed. Radiation. Let's talk about this properly, because this is one of those topics that sounds technical and dry until you understand what it actually means for a human body, and then it becomes one of the most urgent challenges in all of space exploration. Here on Earth, you are protected. You probably don't think about it much, but right now, as you watch this, you are being shielded by 2 remarkable invisible layers. The first is Earth's magnetic field, a massive bubble generated by the churning of molten iron deep inside our planet's core. This magnetic field deflects a huge portion of the charged particles that stream out from the sun in a constant flow called the solar wind. Without it, those particles would strip our atmosphere away over millions of years and bombard the surface with harmful radiation. The second shield is Earth's atmosphere itself, roughly 10,000 kilometers of gas, gradually thinning as you go higher, but still thick enough near the surface to absorb most of the remaining radiation that sneaks through. Together, these 2 layers give you a radiation dose that is manageable. It is in fact part of life on Earth. You get a small dose every day. Your body has spent billions of years of evolutionary history learning to deal with it. But step outside that protective bubble, everything changes. In deep space, the vast emptiness between Earth and Mars, there is no magnetic field wrapping around you. There is no atmosphere overhead. You are fully exposed to 2 primary sources of radiation that are frankly terrifying when you look at them up close. The first is solar particle events. These are massive eruptions from the sun, solar flares and coronal mass ejections that can release enormous bursts of energetic protons in a matter of minutes. If an astronaut is caught outside a spacecraft during one of these events without adequate shielding, the radiation dose can be lethal within hours. These events are somewhat predictable, but not perfectly so. The sun has its moods, and it doesn't always give much warning. The second source is even more insidious: galactic cosmic rays. These are not from our sun at all. They come from outside our solar system, from supernova explosions, from neutron stars, From the violent deaths of stars across the galaxy, they are high-energy particles, mostly protons and atomic nuclei, traveling at close to the speed of light, and unlike solar particles, they cannot really be predicted. They are constant, they are everywhere, and they are extraordinarily difficult to shield against because of how deeply they penetrate matter. Here's a chilling number for you. During the roughly 250 days that the Curiosity rover spent in transit to Mars, tucked inside its protective spacecraft, the radiation detectors on board measured a total dose equivalent to what a radiation worker on Earth is allowed to receive over 5 years. 5 years of radiation exposure in 8 months, and that measurement was taken inside the spacecraft. Astronauts would receive additional doses during surface operations on Mars, where the thin Martian atmosphere, about 1% the density of Earth's, provides almost no protection. NASA's current guidelines say that an astronaut's lifetime radiation exposure should not increase their risk of dying from cancer by more than 3%. A round trip to Mars, including time on the surface, could push right up against, or even exceed, that limit depending on solar activity during the mission. This is not a hypothetical concern. This is one of the central engineering and medical challenges that every serious Mars mission plan has to grapple with. So what do you do about it? There are a few approaches being actively developed, and they range from the elegantly practical to the breathtakingly ambitious. The most straightforward solution is better shielding. Current spacecraft use materials like polyethylene, a type of plastic that is actually more effective than aluminum at stopping certain types of radiation because it contains more hydrogen atoms, and hydrogen is good at absorbing those incoming particles. Researchers are also looking at water walls, literally surrounding the crew's living quarters with tanks of water that serve double duty as both life support supply and radiation barrier. It's clever, efficient engineering. But here's the hard truth about shielding against galactic cosmic rays specifically. These particles are so energetic that making a shield thick enough to stop them completely would make the spacecraft impossibly heavy. There is a physical trade-off that current material science struggles to overcome. So another approach is pharmaceutical, developing drugs that can help cells repair radiation damage more quickly. There is active research into radioprotective agents, compounds that could be taken by astronauts to reduce the biological impact of their radiation exposure. This is still very much a developing field, but it's a genuinely promising one. And then there's the most powerful solution of all: speed. The faster you get to Mars, the less time you spend exposed. If you could cut the transit time from 7 months down to, say, 3 months, or even shorter, you dramatically reduce the cumulative radiation dose. Speed isn't just about convenience on a Mars mission. Speed is a medical necessity. And that brings us to one of the most exciting frontiers in space propulsion technology, because the rockets we use today are, in a cosmic sense, remarkably slow. Let's put that into perspective. The rockets that currently launch spacecraft to Mars use chemical propulsion. Essentially, they burn fuel and expel the exhaust gases at high speed to generate thrust. It's the same basic principle that Wernher von Braun and his team used in the 1940s and 50s. Controlled explosions, enormously energetic, but also enormously inefficient in terms of the energy we actually extract from the fuel. The specific impulse, the measure of how efficiently a rocket uses its fuel, for chemical rockets tops out at around 450 seconds. That sounds abstract, but what it means practically is that you need enormous amounts of fuel to generate relatively modest thrust, and you can only burn it for a short time before you run out. Most of the time on a journey to Mars, a chemically propelled spacecraft isn't thrusting at all. It's coasting, a ballistic arc through space, carried by the momentum of that initial burn and the gentle curve of gravity. Now imagine something different. Imagine a propulsion system that burns far more efficiently, that can thrust continuously for days, weeks, even months. Even a gentle but constant push adds up to extraordinary speeds over time. That system exists. It's called nuclear thermal propulsion, and NASA and other agencies are actively working to bring it to readiness. Here's how it works. Instead of burning chemical propellants to generate heat, a nuclear thermal rocket uses a nuclear reactor to superheat a propellant, typically liquid hydrogen, to temperatures far beyond what any chemical reaction can achieve. The hydrogen expands explosively through a nozzle and generates thrust. The specific impulse of a nuclear thermal rocket is roughly double that of the best chemical rockets, around 800 to 900 seconds. That means twice the efficiency, twice the bang for your fuel. Studies have suggested that nuclear thermal propulsion could reduce the transit time to Mars to somewhere between 3 and 4 months, cut the radiation exposure roughly in half, make the mission significantly safer and more practical. NASA actually had a working nuclear thermal rocket program in the 1960s and 70s called NERVA, Nuclear Engine for Rocket Vehicle Application. The engines were built and tested on the ground. They worked. The program was cancelled for political and budgetary reasons, not technical ones. And now, decades later, the concept is being revisited with modern materials and modern understanding. In 2021, NASA and DARPA announced a joint program called DRACO, Demonstration Rocket for Agile Cislunar Operations, aimed at demonstrating nuclear thermal propulsion in space by the mid-2020s. That program is moving forward. This is not a dream anymore. This is engineering in progress, but nuclear thermal is not even the most ambitious option on the table. There's nuclear pulse propulsion, a concept so audacious it almost sounds like satire. The idea, seriously proposed by physicists in the late 1950s under a program called Project Orion, was to propel a spacecraft by detonating a series of nuclear bombs behind it. The shock waves would push a massive plate, called a pusher plate, at the back of the spacecraft, driving it forward. The physics actually work. Theoretical performance was extraordinary, specific impulses in the tens of thousands of seconds, capable of reaching Mars in weeks rather than months. Freeman Dyson, one of the brilliant physicists who worked on the project, genuinely believed it could be humanity's fastest path to the outer solar system. The program was eventually shut down primarily due to the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. It remains one of the most fascinating might-have-beens in the history of human spaceflight. Then there's ion propulsion, a technology that is not theoretical at all. It's already being used successfully on multiple spacecraft. Ion drives work by using electric fields to accelerate ions, charged particles, to extremely high velocities and expelling them as exhaust. The thrust generated is tiny. We're talking about the equivalent of the weight of a sheet of paper pressing against your hand. But because they are extraordinarily fuel efficient, they can run for months or years, gradually building up speed in a way that chemical rockets simply cannot match. NASA's Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Sirius, used ion propulsion. The Hayabusa missions from the Japan Aerospace Exploration Agency used it to visit asteroids. ESA's Smart 1 lunar orbiter used it. These are proven flight-tested systems for crewed Mars missions. Ion drives aren't quite there yet. They don't produce enough thrust to accelerate a large, heavy crewed vehicle in a practical time frame, at least not with current power sources. But combined with other technologies, particularly nuclear power supplies to generate the electricity the ion drive needs, they become a very compelling part of the future propulsion toolkit. And then there are the truly visionary ideas. The ones that exist right now only as equations and simulations and daring papers in physics journals, but that are grounded in real science, solar sails, laser propulsion, even theoretical concepts like the Alcubierre drive, a hypothetical method of warping space-time itself to achieve faster-than-light travel that general relativity technically does not forbid, though the engineering requirements are currently beyond any conceivable technology. We'll get into some of these more in later sections of this video. But for now, the key takeaway is this. The question of how long it takes to get to Mars is not a fixed answer carved in stone, it is a moving target, a challenge that brilliant minds around the world are actively working to shrink. Every decade of progress in propulsion science, materials technology, and nuclear engineering pushes that travel time lower, potentially far lower. And every reduction in travel time is not just a technical achievement. It is a potential lifesaver for the crew that makes the journey. There's something deeply human about all of this, isn't there? The fact that we identified a danger, cosmic radiation, and instead of giving up, we started asking how to go faster, how to shield better, how to protect the people brave enough to make the trip. We are a species that refuses to be stopped by obstacles. We are a species that looks at a problem and sees a puzzle worth solving. Carl Sagan once wrote that we are a way for the cosmos to know itself. Think about that for a moment. The universe created beings, us, who are now actively trying to cross the space between worlds, not because we have to, not because survival demands it, but because curiosity does. That drive, that irresistible pull toward the unknown, is one of the most beautiful things about being human. Now, here is where we stand after 2 sections of this journey. You understand that the trip to Mars takes roughly 7 months on the most efficient chemical rocket trajectory. You understand that radiation in deep space is a serious medical challenge that makes speed not just desirable, but necessary. And you've gotten your first look at the propulsion technologies, nuclear thermal, ion drives, and beyond. That could dramatically change what's possible, but there's a dimension of this question we haven't fully explored yet. What happens to the human body over 7 months in microgravity? Because space doesn't just bombard you with radiation, it also does something quieter, something more insidious. It begins to take your body apart, bone by bone, muscle by muscle, system by system. And the science of what actually happens to astronauts on long-duration missions, from the International Space Station studies, from Scott Kelly's famous year in space, from Russian cosmonauts who have spent record-breaking time aboard Mir and the ISS, paints a picture that is both sobering and fascinating. That's where we're heading in part 3. Because understanding the full challenge of getting to Mars means understanding not just the physics of the journey, but the biology of the traveler. And trust me, what the human body goes through in deep space is one of the most remarkable stories in all of modern medicine. If you are enjoying this video, make sure to subscribe to the channel. Every video on this channel is built to make you see the cosmos differently. Now, start with a thought experiment. Imagine you wake up tomorrow morning and gravity is gone. Not reduced, not weakened, gone. Your body, which has spent every single second of its existence being pulled toward the center of the Earth, suddenly has nothing to push against, nothing to resist, nothing to work against. At first, it might sound wonderful. No heavy limbs, no aching back. You float effortlessly through your home like something out of a dream. But here's what most people don't realize. Gravity is not just a force that pulls you down, it is a force that keeps you alive. It has shaped every system in your body, your heart, your bones, your muscles, your blood, your brain, over hundreds of millions of years of evolution. And when you take it away, those systems don't just relax. They start to fall apart. This is the hidden enemy of a Mars mission. Not the dramatic Hollywood explosions or asteroid collisions, the slow, quiet, relentless unraveling of the human body in the absence of the force it was built to live inside. Let's start with bones, because the numbers here are genuinely alarming. On Earth, your bones are constantly being remodeled. Old bone tissue is broken down, and new bone is built in its place. A continuous cycle driven in large part by the mechanical stress that gravity and movement place on your skeleton. When you walk, run, carry things, your bones feel that load and respond by maintaining their density and strength. In microgravity, that mechanical load disappears almost entirely. Your skeleton stops receiving the signals it needs to maintain itself, and the result is bone loss at a rate that has no real equivalent in normal human experience. Studies conducted on astronauts aboard the International Space Station, which has given us by far the richest data set on long-duration spaceflight, have shown that astronauts can lose anywhere from 1 to 2% of their bone density per month in key load-bearing areas like the spine, the hips and the upper femur, the thigh bone. Do the math on that for a 7-month trip to Mars. By the time you arrive, you could have lost somewhere between 7 and 14% of your bone density in those critical regions. Then add the time spent on the Martian surface, where gravity is about 38% of Earth's, better than zero, but still far below what your body evolved for. Then add the return trip. Astronauts who've spent 6 months on the ISS have been documented to take months, sometimes over a year, of intensive rehabilitation on the ground before their bone density fully recovers. And some studies suggest that certain bone loss may never be fully reversed. This is not a minor inconvenience. Fragile bones in a crew member who needs to land on Mars, operate in a suit, carry equipment, and respond to emergencies is a genuine safety hazard. Fractures in deep space, far from any surgical facility, could be catastrophic. Now let's talk about muscles. The story here follows a similar pattern, but the timeline is even faster. Muscles atrophy. They shrink and weaken when they aren't used. And in microgravity, you simply don't use most of your muscles the way you do on Earth. You don't need to hold yourself upright. You don't need to support your own weight. The constant, low-level muscular effort that you barely notice in daily life on the ground simply stops. Without intervention, astronauts can lose significant muscle mass, particularly in the legs and lower back, within just a few weeks of entering microgravity. The calf muscles, which on Earth are constantly working against gravity just to keep you standing, can lose over 20% of their volume in as little as 5 to 11 days without exercise. This is why exercise is not optional on the International Space Station. It is mandatory. Astronauts are required to exercise for roughly 2 hours every single day, using specially designed resistance machines and treadmills with harness systems that pull them down toward the treadmill surface to simulate the loading their bones and muscles need. And even with all that effort, some muscle and bone loss still occurs. On a Mars-bound spacecraft, that same discipline will be required. But designing effective exercise equipment that fits inside a vehicle small enough and light enough to be launched from Earth, while also being robust enough to function reliably for 7+ months, is a genuine engineering challenge. Every kilogram of mass on a spacecraft costs an enormous amount of fuel to launch. Every piece of equipment has to earn its place. But here is where things get particularly fascinating and a little unsettling. While your bones and muscles weaken in microgravity, something strange happens to the fluids in your body. On Earth, gravity pulls your blood and other fluids downward toward your legs and lower body. Your cardiovascular system, your heart, your blood vessels have all adapted over your lifetime to pump against that downward pull, to keep blood flowing up to your brain despite gravity working against it. In microgravity, that downward pull disappears, and the fluid redistribution that follows is immediate and dramatic. Within the first few hours of entering weightlessness, blood and bodily fluids shift upward, toward the upper body and head. Astronauts describe it as feeling like a permanent head cold. Their faces puff up slightly, their nasal passages feel congested. They often experience headaches in the early days of a mission. And here's the really serious part. The shift of cerebrospinal fluid, the clear liquid that surrounds and cushions your brain and spinal cord, upward into the skull can increase pressure inside the skull. Researchers studying MRI scans of astronauts before and after long missions have found structural changes in the brain itself. The brain can shift positions slightly within the skull. The optic nerve, which connects the eye to the brain, can become compressed. The shape of the eyeball itself can change. The result, in many cases, is a condition called spaceflight-associated neuroocular syndrome, which can cause significant vision problems. Some astronauts have returned from long missions with noticeably degraded eyesight. In a few cases, the vision changes have been permanent. Think about that for a moment. A crew member on a Mars mission, after months in space, arriving with impaired vision, needing to land a spacecraft, operate complex equipment, navigate an alien surface. This is one of the most active areas of medical research in human spaceflight right now, and it remains one of the least fully understood challenges on the road to Mars. There is also the heart. Your heart is essentially a pump, a muscular organ that has evolved to work hard against the demands of gravity. In space, its workload changes dramatically. The heart doesn't need to pump as forcefully against gravity, and over time, like any muscle, it responds to reduced demand by becoming smaller and less powerful. Studies have shown measurable decreases in heart muscle mass during long-duration spaceflight. Beyond that, the cardiovascular system, the whole network of blood vessels throughout your body, adapts to the reduced demands of weightlessness in ways that can leave astronauts vulnerable when they return to gravity. A condition called orthostatic intolerance is common, the inability to stand upright without feeling dizzy or faint, because the cardiovascular system has lost some of its ability to quickly compensate for the demands of standing in a gravitational field. For an astronaut landing on Mars after 7 months in space, this matters enormously. Mars has gravity, 38% of Earth's. That's not nothing. Your body will feel it. And a cardiovascular system that has spent 7 months adapting to weightlessness will suddenly need to deal with that gravitational load again immediately upon arrival, before the crew has had any time to recover and readapt. The landing day on Mars might actually be one of the most physically demanding and medically risky moments of the entire mission. Now, let's layer on one more challenge. One that doesn't get nearly as much attention as radiation or bone loss, but that space medicine researchers regard as critically important: the immune system. Multiple studies have shown that spaceflight causes measurable changes in immune function. Certain immune cells, particularly natural killer cells, which are part of your body's first line of defense against viruses, bacteria, and even cancer cells, show reduced activity during spaceflight. At the same time, latent viruses that live dormant inside your body, can reactivate in space. The chickenpox virus, the Epstein-Barr virus, the herpes simplex virus. These can wake up under the stress of spaceflight and begin shedding, even in astronauts who have had no symptoms for decades on the ground. The psychological stress of long confinement, isolation, and the constant low-level anxiety of operating in a dangerous environment all contribute to immune suppression as well. The border between the physical and psychological challenges of deep spaceflight is blurry. They feed into each other in complex ways that researchers are only beginning to fully map. This brings us to the psychological dimension, and it is enormous. We have some remarkable data from analog studies, experiments designed to simulate the psychological experience of long-duration spaceflight, without actually going to space. The Mars 500 study, conducted between 2010 and 2011, saw 6 volunteers sealed inside a facility in Moscow for 520 days, the approximate duration of a Mars mission including surface time. 520 days with no fresh air, no open sky, no real privacy, no way to escape the same small group of people, the same walls, the same routine. The results were fascinating and sobering. All participants completed the mission, which is remarkable in itself. But the study documented significant sleep disruption, reduced physical activity, sedentary behavior that increased over time, and in some crew members, symptoms consistent with depression and psychological withdrawal. One participant effectively shut down socially during the final months of the simulation, becoming increasingly isolated from the rest of the crew, despite being physically confined with them. Real-world data from long-duration ISS missions paints a similar picture. Astronauts report that the middle phase of a long mission, not the exciting beginning or the anticipated end, but the long, monotonous stretch in between, is psychologically the most difficult. The novelty has worn off. The end is not yet in sight. You are surrounded by the same people in the same space, day after day, performing the same routines. And for a Mars mission, this psychological challenge would be compounded by something that has no precedent in human history: true isolation. Every human being who has ever been in space has been able to look out the window and see Earth. The International Space Station orbits just 400 kilometers above the surface. Earth fills the window. It is right there, beautiful, familiar, home. On the way to Mars, Earth shrinks and keeps shrinking until it is just a point of light, a pale blue dot. To borrow the immortal phrase that Carl Sagan used to describe the famous photograph taken by Voyager 1 in 1990 as it swept through the outer solar system. That image, Earth captured from a distance of about 6 billion kilometers, appearing as a tiny fraction of a pixel suspended in a sunbeam, is one of the most profound photographs ever taken. Sagan's reflection on it remains one of the most powerful pieces of scientific writing in human history. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, that all of human history, every king and emperor, every saint and sinner, every mother and child, played out on a mote of dust suspended in a sunbeam. The crew of a Mars mission will look out their window and see that pale blue dot, and they will know with an immediacy that no photograph can fully capture, that all of humanity, every person they have ever loved, every city they have ever walked through, every ocean, every mountain, every living thing is contained in that tiny, fragile pinprick of light. The psychological impact of that realization, living with it, not as a thought experiment but as a daily reality, is something we genuinely do not fully understand yet. It might be humbling in a way that deepens purpose and resolve. It might, for some individuals, be destabilizing in ways that are difficult to predict. Space agencies are working hard on crew selection, psychological support systems, communication strategies, and even virtual reality tools that might allow crew members to immerse themselves in Earth environments as a form of mental relief during the long journey. The Japanese Space Agency has conducted research into what they call ikioi, the vitality and sense of energy that comes from positive social interaction, as a key factor in crew mental health. But here's the thing. Here's the part of this story that fills me with something close to awe. We know all of these challenges, every single one of them. The bone loss, the muscle atrophy, the fluid shifts, the vision changes, the immune suppression, the psychological weight of isolation, the radical aloneness of looking back at a shrinking Earth. We know. And we are not stopping. Instead, the global community of space medicine researchers, engineers, psychologists, and mission planners is attacking every single one of these problems with incredible creativity and determination. countermeasure by countermeasure, study by study, data point by data point, because the people who will one day make this journey are not reckless thrill seekers. They are not sacrificing themselves carelessly. They are making an informed choice, as explorers always have, to push beyond the known boundary, to accept risk in exchange for discovery, to carry the rest of humanity forward on their shoulders. There is something ancient and timeless about that choice. It echoes the first human beings who built boats and pushed beyond the horizon of familiar coastlines. The adventurers who crossed mountain ranges not knowing what lay on the other side. The scientists who first proved that the Earth was round, or that it orbited the Sun, at a time when those ideas were not safe ones to have. We have always been a species that moves toward the unknown. Mars is just the next horizon. We've now covered radiation, propulsion, bone and muscle loss, cardiovascular changes, immune function, and the profound psychological challenge of deep space isolation. That's the full weight of what the human body faces on a 7-month journey to Mars. And yet, there's something we still haven't fully addressed, something that might be the most important variable of all. What happens when you actually get there? Because landing on Mars is arguably more dangerous than the journey itself. The thin atmosphere makes parachutes far less effective. The surface is alien and uncharted. The dust, fine, pervasive, potentially toxic Martian dust, gets into everything. And the clock starts immediately. You have supplies, power systems, habitats to deploy, and no rescue if something goes wrong. The engineering of Mars arrival, and the extraordinary ingenuity that has already gone into landing robots there, is a story that deserves its own deep dive. 7 minutes of terror. That's what NASA engineers themselves called it. Not journalists, not science communicators trying to make it sound dramatic for television. The actual engineers who designed the system, the people who spent years of their lives building it, testing it, losing sleep over it, looked at what they had created and said, 7 minutes of terror. And when you understand what happened during those 7 minutes, you will completely agree with them. Because landing on Mars is not like landing anywhere else. It is a uniquely brutal engineering problem, one that sits in a kind of cruel middle ground that makes it harder than landing on the Moon and harder than landing back on Earth. And the fact that we have successfully done it multiple times already is, in the honest assessment of anyone who understands the physics involved, nothing short of extraordinary. Let's walk through it together. First, you need to understand what Mars's atmosphere actually is, because it is the root of almost everything that makes landing there so difficult. Mars has an atmosphere. That's the good news. Unlike the Moon, which has essentially no atmosphere at all, Mars has a thin layer of gas, mostly carbon dioxide, about 95%, with small amounts of nitrogen, argon, and trace gases. This atmosphere creates a small amount of aerodynamic drag, which means you can, in principle, use it to slow down an incoming spacecraft. That's the idea behind aerobraking, using atmospheric friction to shed speed without burning fuel. Here is the bad news. That atmosphere is roughly 100 times thinner than Earth's at the surface, 1% of Earth's atmospheric density, which means it creates just enough drag to be useful, but nowhere near enough to do the job on its own. Think about it this way. When a spacecraft enters Earth's atmosphere, the thick air creates enormous friction that slows the vehicle dramatically over a relatively long period of time. The heat shields on returning Apollo capsules and modern spacecraft glow white-hot as they convert that kinetic energy into heat, but they work. The atmosphere does enough of the heavy lifting to bring the spacecraft from orbital velocities down to speeds where parachutes, and eventually rockets or airbags, can handle the final descent and landing. On Mars, you get a fraction of that braking. The atmosphere slows you down some, but not nearly enough. You arrive at the top of the Martian atmosphere traveling at something like 20,000 kilometers per hour. By the time you've burned through the thickest part of the atmosphere, you might be down to around 1,500 kilometers per hour. Still far too fast to land, still fast enough to be lethal on impact. And here's the truly cruel twist. You're low enough in the atmosphere that you don't have much altitude left to work with. The window between too high for rockets to be efficient and too low to survive without them is frighteningly narrow. You have to solve the entire remaining problem, going from 1,500 kilometers per hour to zero in a very short distance and a very short time. 7 minutes. From the top of the atmosphere to the surface. 7 minutes to go from 20,000 kilometers per hour to a gentle, controlled landing. 7 minutes during which the spacecraft is entirely on its own, because the signal delay between Mars and Earth means that by the time mission control even receives confirmation that the spacecraft has entered the atmosphere, it has already landed or crashed. There is no intervention possible, no human hand on any joystick. The spacecraft either executes its pre-programmed sequence flawlessly or it doesn't. The history of attempts to land on Mars underscores just how hard this is. Of the roughly 50 missions that have been sent to Mars over the decades by the United States, the Soviet Union, Europe, China, India, the United Arab Emirates, and others, a significant number have failed. Some failed at launch, some were lost in transit, some reached Mars and then went silent at the worst possible moment. The Soviet Union's Mars program in the early 1970s sent multiple landers, and while some achieved orbit successfully, surface landings were plagued with problems. Mars 2 crashed, Mars 3 touched down, the first spacecraft ever to land on Mars, but stopped transmitting after just 20 seconds. 20 seconds of data from the Martian surface and then silence. To this day, no one knows exactly why NASA's Viking program in 1976 achieved the first fully successful Mars landings. Viking 1 and Viking 2 both touched down safely and sent back data for years. Viking 1 operated for over 6 Earth years, an extraordinary achievement for the era, but failures continued in subsequent decades. The Mars Climate Orbiter in 1999 was lost due to a unit conversion error. One engineering team was using metric units and another was using imperial. A mismatch between metric and non-metric measurements sent a spacecraft worth $327 million into the Martian atmosphere at the wrong angle. It burned up. The Mars Polar Lander, also in 1999, is believed to have crashed due to a software error that caused its descent engines to shut off prematurely. Beagle 2, a British lander that was part of ESA's Mars Express mission, reached the surface in 2003 but failed to fully deploy its solar panels, leaving it unable to communicate. It lay silent and unseen on the Martian surface until NASA's Mars Reconnaissance Orbiter photographed it from orbit in 2015. There it was, lying on the ground just a few kilometers from its intended landing site, solar panels partially open, tantalizingly close to success. But here is where the story turns triumphant. Because when the engineering works, when the years of planning and testing and iteration pay off, what happens is genuinely one of the greatest technological achievements in human history. Let me take you through the Curiosity rover landing in 2012 because it remains one of the most audacious and successful engineering feats ever attempted. The engineers at NASA's Jet Propulsion Laboratory faced a problem. Curiosity was big, much bigger than the previous Spirit and Opportunity rovers, which had used a brilliantly clever airbag system, bouncing across the Martian surface like an enormous beach ball until they rolled to a stop. But Curiosity weighed about 900 kilograms. You cannot land 900 kilograms with airbags. The math simply doesn't work, so they invented something entirely new. Something so complex and unlikely looking that when it was first presented to NASA management, the engineers who designed it were apparently asked if they were joking. They called it the Sky Crane. Here is how it worked. The spacecraft entered the Martian atmosphere protected by a heat shield. Just like previous missions, parachutes deployed at supersonic speeds, a jaw-dropping feat of engineering in itself, since supersonic parachute deployment creates forces that would rip apart almost any conventional design. The heat shield fell away. Retro-rockets fired to slow the descent further, and then, at roughly 20 meters above the surface, something unprecedented happened. The descent stage, the rocket-powered platform carrying the rover, slowed to a hover, and from it, on a set of nylon bridles and an electrical umbilical cord, the Curiosity rover was lowered on cables toward the surface, gently, precisely, like a crane lowering a load onto a construction site. Except this crane was hovering on rockets on another planet, in an autonomous sequence that had to work perfectly the first time with no possibility of human intervention. When the rover's wheels touched the Martian surface, sensors detected the contact. The cables were cut. The descent stage flew off to one side and crashed at a safe distance, and Curiosity was sitting on Mars, intact, ready to work. The entire sequence, from atmospheric entry to surface contact, took approximately 7 minutes, and it worked flawlessly on the first attempt. When the confirmation signal arrived at Mission Control in Pasadena, California, delayed by about 14 minutes because of the distance between Earth and Mars at that moment, the room exploded. Scientists and engineers who had dedicated years or even decades of their lives to that mission were weeping, hugging, jumping up and down. The footage of that moment is one of the most purely joyful things you will ever watch. Brilliant people at the absolute limit of what human technology can achieve, finding out that they had done it. Perseverance, landing in 2021, used essentially the same Sky Crane system, and again it worked perfectly. That moment, repeated twice now, and likely to be repeated again with future missions, is a reminder of something important. When we talk about the challenges of getting to Mars, we should also remember to celebrate what we have already accomplished. We have landed complex, functional robots on the surface of another world multiple times. We have driven them across alien terrain, drilled into Martian rock, scooped up Martian soil, and listened to Martian wind with microphones. Perseverance even deployed a small helicopter named Ingenuity, which became the first powered aircraft to fly on another planet. It was designed to fly 5 times as a technology demonstration. It flew 72 times before its mission officially ended in early 2024, 72 flights on Mars, with a helicopter the size of a tissue box. But here is the critical difference between landing a rover and landing a crewed spacecraft. Rovers are small, relatively light, manageable within the constraints of current technology, even if only barely. A crewed Mars lander would be an entirely different beast. Think about everything you need to keep humans alive: the habitat module, the life support systems, oxygen generation, carbon dioxide scrubbing, water recycling, the food supplies for the surface stay and the return journey, the power systems, the pressurized suits, the scientific equipment, the return vehicle. We're talking about a landed mass potentially in the range of 20 to 40 metric tons or more, depending on the mission architecture. That is an order of magnitude beyond anything we have ever landed on Mars. The Sky Crane system that so elegantly solved the Curiosity problem cannot simply be scaled up to handle that kind of mass. New solutions are needed, fundamentally different approaches. SpaceX's Starship, the enormous, fully reusable launch vehicle that has been undergoing development and testing throughout the early 2020s, is designed with Mars in mind from the ground up. Its architecture envisions using the Martian atmosphere for aerobraking, then using its own powerful Raptor engines to perform what is called a propulsive landing, essentially hovering on rockets all the way to the surface. The engineering challenges of doing this at Mars scale, with a vehicle the size of a 12-story building in an atmosphere that provides limited aerodynamic assistance, needing to produce and store propellant on the Martian surface for the return trip, are immense. But SpaceX is actively developing and testing these technologies. The Starship system has shown remarkable progress in its test flights, going from spectacular unplanned rapid disassembly, their charmingly euphemistic way of describing explosions, to successful flight and recovery in the span of just a few years. There's another approach worth understanding, one that has been seriously studied by NASA and independent researchers for decades: in situ resource utilization, ISREL for short. The idea is elegant in its ambition. Don't carry all your return fuel from Earth. Make it on Mars. Mars's atmosphere is 95% carbon dioxide. The Sabatier reaction, a well-understood chemical process, can combine carbon dioxide with hydrogen to produce methane and water. Methane is a rocket propellant. Water can be electrolyzed into hydrogen and oxygen, more propellant and breathable air. The Perseverance rover is actually conducting a small-scale demonstration of this right now. An instrument called MOXIE, Mars Oxygen in Situ Resource Utilization Experiment, has successfully produced small amounts of oxygen directly from the Martian atmosphere. It is the first time oxygen has ever been produced on another planet, a proof of concept that, scaled up enormously, could supply both breathable air and rocket propellant for a crewed mission. If you can produce your return fuel on Mars using Martian resources, you don't have to launch it from Earth. And that changes the economics and logistics of the mission dramatically. Instead of carrying the return propellant all the way from Earth, a massive additional weight that requires more fuel to launch, which requires more fuel to produce, in a cascading cycle that mission planners call the tyranny of the rocket equation. You send a fuel production facility to Mars in advance, let it fill up a waiting return vehicle, and only then send your crew. By the time the astronauts arrive, the return vehicle is already fueled and ready. They don't have to produce everything themselves under time pressure on the surface. It's a beautiful piece of mission planning, and MOXIE has taken the first real step toward making it reality. Now here's something that doesn't get discussed nearly enough when people talk about landing on Mars: dust. Martian dust is pervasive in a way that is genuinely difficult to convey. It covers essentially the entire surface. It hangs in the atmosphere in quantities that give the Martian sky its characteristic butterscotch color, that pale, washed-out reddish-orange that Martian sunsets and sunrises display so hauntingly in photographs from the surface. It gets into everything. Dust storms on Mars can be truly planetary in scale. The kind of storm that swallowed the Opportunity rover in 2018, blocking enough sunlight to drain the solar-powered rover's batteries to the point of no return, was a global event. Dust that high in the atmosphere, blocking that much sunlight across an entire planet for a crewed mission, this creates multiple layers of concern. Solar panels, a primary power source for many proposed mission architectures, lose effectiveness when coated in dust or when sunlight is blocked by storm activity. The dust itself is chemically reactive in ways that are still being studied and may pose health risks if inhaled or if it gets inside habitats. It is electrostatically charged, which means it clings stubbornly to suits and equipment, and landing during or shortly after a major dust storm. The reduced visibility and changed atmospheric density could affect the precision of a landing in ways that are difficult to plan for. These are not unsolvable problems, but they are real ones, and any serious Mars mission plan has to account for them thoroughly. There's a word I keep coming back to as I walk through all of this. That word is ingenuity. Not just the helicopter, though that little machine is a perfect symbol of it, but the broader human quality, the stubborn, creative, endlessly iterative problem-solving that has gotten us from Sputnik in 1957 to a helicopter flying on Mars in 2021, 64 years. In the sweep of human history, that is nothing less than a single lifetime. What the engineers and scientists of this era have accomplished is something that would have seemed like pure fantasy to the people who watched Sputnik's radio signal bleep overhead. And yet here we are, landing robots with sky cranes, growing oxygen from Martian air, listening to Martian wind. The universe has been around for nearly 14 billion years. Human civilization has existed for perhaps 12,000 years. The space age is less than 70 years old. And in those 70 years, less than the lifespan of many people alive today, we have gone from never having left the ground to having our machines on 4 other worlds and in interstellar space. We are extraordinary creatures, fragile, uncertain, constantly making mistakes, but extraordinary. And when we are at our best, when we channel our ingenuity and our courage and our collaboration toward a shared goal, there is essentially nothing we cannot eventually figure out. Mars is the next test of that, the biggest one we have ever attempted. So where does all of this leave us? We've now traveled through the physics of the journey, the Hohmann transfer, the launch windows, the 7 months of transit. We've felt the weight of what that journey does to the human body, the radiation, the bone loss, the cardiovascular changes, the psychological isolation. And now we've stood at the edge of the Martian atmosphere and felt the terror and triumph of those 7 minutes of entry, descent, and landing. But there's a question we haven't asked yet. One that might be the most important question of all: why? Why spend the extraordinary resources, the money, the time, the human risk to send people to Mars when we could send more robots? When we could spend that money on problems right here on Earth? It's a question that deserves a serious, honest answer, one that goes beyond the romantic pull of exploration and engages with the real strategic, scientific, and philosophical arguments on all sides. And then, beyond why, there's the question of when. What is the realistic timeline? Not the optimistic press release version, the honest, evidence-based assessment of where the technology actually is, what the remaining challenges actually are, and what it would genuinely take to put a human being on Mars within the next few decades. That's what we will cover now, because the answer is more nuanced and in some ways more hopeful than most people expect. Why Mars? It sounds like a simple question, and depending on who you ask, you'll get wildly different answers. An aerospace engineer will talk about orbital mechanics and launch windows. A planetary scientist will talk about ancient riverbeds and the search for life. A philosopher might talk about the nature of human curiosity and our deep, almost genetic compulsion to explore. Elon Musk will tell you it's about making humanity multiplanetary, about survival insurance for our species against existential catastrophe. All of those answers contain truth, but none of them, on their own, fully captures why Mars, specifically Mars, out of all the destinations in the solar system, has become the focus of so much energy, so much funding, so much imagination. So let's actually dig into it. Let's be honest, rigorous, and open-minded about this, because the case for going to Mars is stronger than many people realize, and the counter-arguments deserve to be taken seriously too. Start with the scientific case, and it is genuinely compelling. Mars is not just a rock in space. It is a world with a history, a long, complex, geologically and potentially biologically rich history that we have only barely begun to read. And reading that history could tell us things about the nature of life in the universe that no other investigation currently available to us can match. Here is what we know. Mars today is cold, dry, and largely inhospitable. Its average surface temperature is around -60 degrees Celsius. Its thin atmosphere provides almost no protection from radiation. Liquid water cannot exist stably on the surface under current conditions. The atmospheric pressure is so low that water would almost instantly boil away or freeze. But Mars was not always like this. Roughly 3 to 4 billion years ago, Mars appears to have been a dramatically different world. Orbital observations and surface data from rovers have revealed ancient river channels carved by flowing water, delta formations where rivers emptied into what were once lakes or seas, mineral deposits, clays, carbonates, sulfates that form in the presence of liquid water, evidence of a thicker atmosphere in the past, a stronger magnetic field, and conditions that, by current scientific understanding, would have been compatible with life as we know it. For perhaps 1 billion years or more, early Mars may have been warm and wet enough to support microbial life. And here's the question that makes astrobiologists lose sleep with excitement. If life arose on early Mars, even simple, microbial life, where did it go? Life, once it gets a foothold, is remarkably persistent. Microbes on Earth survive in conditions that would kill most multicellular organisms, in highly acidic hot springs, in the frozen depths of Antarctic ice, kilometers underground in solid rock, in environments saturated with radiation. Some organisms can even survive brief exposure to the vacuum of space. Could Martian life have survived? Could it have retreated underground as the surface became inhospitable, following liquid water down into subsurface aquifers or hydrothermal systems, where some models suggest liquid water may still exist today? Could Mars right now harbor microbial life beneath its surface? We genuinely do not know. And that uncertainty is one of the most profound open questions in all of science. The Perseverance rover is actively searching for biosignatures, chemical and physical traces that could indicate past life, in a location called Jezero Crater, which was once a lake fed by river systems. It has been collecting rock core samples and sealing them in small titanium tubes, caching them on the surface for a future sample return mission to bring back to Earth laboratories for analysis. But here is the honest limitation of robotic exploration. Robots are slow. They are limited in where they can go, what they can sense, and how quickly they can respond to unexpected findings. A human geologist standing in Jezero Crater, able to pick up rocks, chip away at surfaces, smell the dust, notice subtle textures and patterns that no camera algorithm has been programmed to look for, could potentially accomplish in a single afternoon what a rover takes months to do. This is not a dismissal of robotic science. The rovers have been extraordinary, but human presence on Mars would supercharge our ability to answer the question of Martian life. And that question might be the most important scientific question of our era, because if we find evidence that life arose independently on Mars, that tells us something staggering about the universe. It tells us that life, given the right conditions, is not a miraculous accident. It is what matter does. Then there's the argument about what Mars teaches us about Earth. Mars and Earth formed from the same cloud of gas and dust roughly 4.5 billion years ago. They are, in a cosmic sense, siblings, products of the same solar system, the same raw ingredients, the same early history. And yet they turned out so differently. Earth is vibrant, warm, covered in liquid water, teeming with life. Mars is frozen, thin, barren, as far as we can tell from the surface at least. Understanding why these two siblings diverged so dramatically gives us profound insight into what makes Earth the way it is. What conditions are truly necessary for a world to remain habitable over billions of years? What role did Earth's magnetic field play? Its larger moon? Its plate tectonics? These questions are not just academically interesting. They are deeply relevant to understanding climate change, planetary habitability, and the long-term future of our own world. Mars is, in a very real sense, a natural laboratory for understanding Earth. Now let's take the philosophical and strategic arguments seriously. The idea of making humanity multiplanetary, of establishing a permanent human presence on another world so that a single catastrophic event cannot end our species, is sometimes dismissed as elite escapism, a way for billionaires to avoid dealing with Earth's problems by fantasizing about starting over on another planet. That criticism has merit as a social critique. But the underlying logic of the multiplanetary argument is actually quite sound when examined carefully. Extinction-level events are not hypothetical. They have happened before, and they will happen again. The asteroid impact that wiped out the non-avian dinosaurs 66 million years ago released energy equivalent to roughly 10 billion nuclear weapons. It fundamentally reshaped life on Earth in a geological instant. We humans, the inheritors of the tiny mammals that survived that catastrophe, exist partly because of an asteroid that hit the Yucatan Peninsula. Supervolcanic eruptions, nearby gamma-ray bursts from dying stars, engineered pandemics, nuclear war. These are not science fiction scenarios, they are real risks on varying timescales. No single one of them is likely in any given human lifetime, but over thousands or millions of years, the probability of at least one civilization-threatening event becomes significant. A civilization confined to a single planet is, in the long run, a civilization with a finite clock. A civilization spread across two or more worlds is dramatically more resilient. Not immortal, nothing is immortal in a universe governed by entropy, but far less fragile. Carl Sagan wrote about this. Stephen Hawking spoke about it. The argument is not new, but it has gained urgency as our understanding of both the risks to Earth and the feasibility of Mars settlement has deepened. Now, the counterarguments, they deserve an honest hearing, because dismissing them would be intellectually dishonest. The most powerful counterargument is the cost and opportunity cost question. Sending humans to Mars safely will cost somewhere in the range of hundreds of billions of dollars over the course of the program, depending on whose estimates you use and how you structure the mission architecture. That is an enormous sum, and here on Earth there are profound urgent problems: poverty, disease, climate change, education, clean water access that could benefit enormously from comparable investment. Is it morally justifiable to spend that kind of money sending people to Mars when millions of children die every year from preventable diseases? This is a question I think every honest Mars advocate has to sit with. And the answer, if there is one, is not simple. Part of it is that space exploration and solving Earth's problems are not actually a zero-sum choice. The technologies developed for space have historically generated enormous economic and practical returns. Satellite communications, GPS, water purification technology, weather forecasting, medical imaging. The list of technologies that trace their development back to space programs is long and genuinely life-improving. But beyond the practical spin-offs, there is a philosophical dimension. Human civilizations have always invested in things beyond immediate survival necessity, in art, in science, in exploration, in understanding. The question is not simply, can we afford to go to Mars, but also, what kind of civilization do we want to be? A species that turns inward and addresses only immediate needs, or one that maintains its reach toward the unknown, even while working on its problems at home? That debate is real, ongoing, and important, and reasonable people can land in different places on it, all right? Now let's talk about when, because this is where the conversation gets most interesting and most contested. Elon Musk has, at various points, suggested timelines for crewed Mars missions that range from the late 2020s to the early 2030s. He has described wanting to establish a self-sustaining city on Mars within the next few decades. These are ambitious timelines, to put it mildly. NASA's official planning has been somewhat more conservative. The agency has spoken about crewed Mars missions in the late 2030s or 2040s. Though those timelines are heavily dependent on funding, political will, and the success of intermediate missions like the Artemis program, which is working to return humans to the Moon as a stepping stone and testing ground for Mars mission technologies, the Moon is not a detour, it is a rehearsal, a place to practice long-duration surface operations, test life support systems, develop in-situ resource utilization techniques, and learn hard lessons about deep space human operations without being quite as far from home as a Mars crew would be. China's space agency has also stated ambitions for Mars exploration, including potential crewed missions in the 2030s to 2040s timeframe. The Tianwen-1 mission, which successfully placed a rover on Mars in 2021, making China only the second nation after the United States to successfully operate a rover on the Martian surface, demonstrated a significant leap in Chinese deep space capability. We are genuinely in a new space race, but this one has a different character from the Apollo-era competition between the United States and the Soviet Union. It is broader, more complex, involving more nations and more private actors, and at least in its public framing, is as much about scientific achievement and long-term settlement as it is about geopolitical prestige. So what does a realistic timeline actually look like? Let's build one from the ground up, based on where the technology and the missions actually stand right now. In the near term, the late 2020s, the most plausible developments include the completion of NASA and ESA's Mars Sample Return mission, which aims to retrieve the rock samples that Perseverance has been collecting and bring them back to Earth for analysis in terrestrial laboratories. This mission has faced significant budget challenges and timeline slippage, but it remains one of the highest scientific priorities in planetary science. SpaceX continues to develop Starship, a vehicle that is explicitly designed in its architecture for Mars missions. The pace of Starship development has been faster than almost any comparable aerospace program in history, though it has also been chaotic, dramatic, and punctuated by spectacular failures as well as equally spectacular successes. By the late 2020s, if development continues at its current trajectory, Starship could be demonstrating cargo delivery to Mars, sending supplies and equipment in advance of crewed missions. In the medium term, the early to mid-2030s, a crewed Mars mission becomes technically plausible if everything goes well. Not certain. Plausible. The distinction matters. Everything going well means Starship or an equivalent heavy lift system achieving reliable operation. It means life support systems proving themselves on long-duration missions in the lunar vicinity. It means the medical countermeasures for radiation and physiological deconditioning reaching sufficient effectiveness. It means international or commercial funding structures that can sustain the program through changes in political administration. Any one of those conditions failing to materialize pushes the timeline back. All of them need to align. That's why experienced space policy analysts tend to be somewhat cautious about the most optimistic timelines, even while acknowledging that the overall direction of travel is genuinely toward Mars. But here's something remarkable that doesn't always make it into these conversations. The pace of progress in the last decade has been faster than in any comparable period since the Apollo era. Reusable rockets, which seemed like an engineering fantasy to many people just 15 years ago, are now operational and routine. SpaceX lands and reuses orbital-class boosters with a reliability that was once considered impossible. Blue Origin, Rocket Lab, and other companies are developing their own reusable systems. The cost of getting mass to orbit has dropped dramatically and continues to drop. Meanwhile, advances in artificial intelligence, materials science, additive manufacturing, biotechnology, and autonomous systems are all converging on spaceflight, in ways that would have seemed like wishful thinking a generation ago. Three-dimensional printing of rocket components, AI-driven mission planning and autonomous spacecraft operation, genetic research into radiation resistance, microbiome management for astronaut health in space. We are not just moving toward Mars at a steady walking pace, we are accelerating. The slope of progress is steepening, and that matters enormously because many of the hardest remaining challenges, particularly in propulsion and radiation protection, are the kinds of problems that yield to sustained technological pressure. They are not fundamental physics barriers, they are engineering problems, and humanity has a very, very good track record of solving engineering problems when it commits to doing so. There's one more dimension of the when question that deserves attention, and it connects back to something we touched on earlier in this video, the human element. The first people to walk on Mars are almost certainly alive right now. Think about that for a moment. Somewhere on this planet, there are young men and women, maybe in their 20s or 30s today, who will one day stand on Martian soil and look back at the pale blue dot of Earth hanging in an alien sky. They might be students right now. They might be pilots or engineers or doctors. They might be watching a video like this one, feeling the same pull of curiosity and wonder that drives this whole conversation. The history of exploration is full of these moments, where the people who would make the leap were already walking around, already dreaming, already preparing, without yet knowing that they were the ones who would be chosen for the defining journey of their generation. That is a staggering thought to sit with. The first human footsteps on Mars, a moment that will be remembered as long as human civilization exists, are waiting in the future of someone who is alive today. And what will those first footsteps mean? Not just practically, not just scientifically. What will they mean for us, for the 8 or 9 or 10 billion people who will watch from Earth as a human being descends the ladder of a Mars lander and touches alien ground for the very first time? I think it will be one of the most unifying moments in human history. More unifying even than Apollo 11, because this time the whole world will be watching in real time with social media and streaming and technology that brings the moment into every home, every phone, every conscious mind that chooses to look up. And in that moment, regardless of what nation built the spacecraft, regardless of what political ideology was in power when it launched, regardless of every division and argument and conflict that occupies so much of our daily attention, in that moment, we will all feel it. We did that. We human beings reached another world, not a robot, not a probe, a person, flesh and blood and bone, shaped by the same evolutionary pressures that shaped every human who ever lived, standing on soil that no foot has ever touched before. It will be the clearest possible statement that we are capable of more than our worst impulses, that the same intelligence and determination that we so often turn toward conflict and destruction can be turned towards something magnificent. We are made of stardust. Every atom in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, was forged in the heart of a star that lived and died before our sun was born. When that star reached the end of its life, it exploded in a supernova, a detonation so powerful it briefly outshone entire galaxies and scattered its contents across the cosmos. Those atoms drifted through space for billions of years before gravity gathered them into a new solar system, a new planet, and eventually, somehow, miraculously, into you. You are the universe looking at itself, thinking about itself, asking questions about itself, and right now, you are watching a video about the day we will reach another world. That is extraordinary. Genuinely, profoundly extraordinary. We have covered so much ground across these first 5 parts. The physics of the journey, the biology of the traveler, the terror and triumph of landing, the arguments for why we go, and the honest assessment of when. We have let the weight of it settle, and we have let the wonder of it rise. But here's what's waiting in the second half of this video, and I want you to feel the pull of it. We haven't talked yet about what happens after you land, the day-to-day reality of living on Mars, the strange and brutal and beautiful experience of being a human being on a world that was not designed for you. The habitats, the food, the suits, the daily routines, the science you would actually do, the sounds you would hear or not hear, the color of the sky at different times of day. And we haven't talked about the return journey, because getting home from Mars is, in some ways, even harder than getting there. And we definitely haven't talked about what comes after the first mission. Because if the first crewed Mars landing is the beginning of something rather than the end, if it is the first chapter of a much longer story, then where does that story go? What does a permanent Mars settlement actually look like? What are the ethics of terraforming another world? What happens to human identity and culture when some portion of humanity is living permanently on another planet? These are the questions that will define the next century of human civilization, and we're going to dig into all of them. Let's do something different to start this section. Close your eyes for a moment. Actually do it, just for a few seconds, and imagine this. You've landed. The 7 months of transit are behind you. The 7 minutes of terror are behind you. Your heart is still hammering from the landing. Your body is readjusting to gravity after months of weightlessness. Even the gentle 38% pull of Martian gravity feels strange and heavy after so long in microgravity. Your legs are uncertain. Your inner ear is confused. But you are here. You are actually here. You walk to the small porthole window of your habitat and you look out. And for the first time in human history, a conscious mind is taking in the Martian landscape not through a camera lens transmitted across millions of kilometers of space, but directly, with human eyes. In real time, what do you see? The sky is not blue. That's the first thing that strikes you. After a lifetime of blue skies, the familiar, comforting azure of Earth's nitrogen and oxygen atmosphere scattering sunlight, the sky over Mars is a pale, dusty butterscotch, a muted pinkish-tan color that shifts toward blue near the horizon during the day and turns an eerie, ethereal blue around the sun at sunset, the exact opposite of Earth, where sunsets paint the horizon red and orange. The reason for this reversal is beautiful in its physics. On Earth, our atmosphere scatters shorter blue wavelengths of light in all directions, which is why the whole sky appears blue. At sunset, sunlight passes through more atmosphere, scattering away the blue and leaving the longer red wavelengths. On Mars, the fine dust particles in the atmosphere are sized just right to scatter red wavelengths more effectively, giving the daytime sky its tan color. Near the sun, where you're looking through less of the dusty atmosphere, the blue light that isn't scattered comes through, giving Martian sunsets their haunting blue glow. The landscape stretches out in front of you in shades of rust and ochre and pale brown. Depending on where you've landed, you might see a flat, rock-strewn plain extending to a horizon that feels surprisingly close. Mars is a smaller planet than Earth, so the horizon curves away faster. Or you might see the distant rise of ancient volcanic plains, or the eroded lips of a crater, or the layered walls of a canyon that would dwarf anything on Earth. The light is dimmer than you're used to. Mars orbits roughly 1.5 times farther from the Sun than Earth, which means it receives about 43% of the solar energy that Earth gets. Midday on Mars is something like late afternoon on a slightly overcast day on Earth. Bright enough to see clearly, but with a quality to the light that feels different, cooler, more distant, and it is completely, absolutely, profoundly silent, not the silence of a quiet room, or a forest at dawn, or a library after closing. This is the silence of a world where no bird has ever called, No wind has ever rustled leaves, no ocean has ever broken on a shore. The Martian atmosphere is too thin to carry sound effectively. The speed of sound on Mars is about 240 meters per second, compared to 343 meters per second on Earth, and many frequencies that human ears are tuned to would be difficult or impossible to hear. Perseverance's microphones have recorded Martian sounds, wind gusts, the whir of its own mechanisms, even the faint buzz of the Ingenuity helicopter's rotors, which was surprisingly difficult to hear even from just a few meters away because the thin air carries so little acoustic energy. On Mars, you could stand next to a helicopter and barely hear it. The silence would be one of the most visceral and disorienting aspects of being there, a silence so complete it has a texture, a silence that your brain, wired for a living world full of sound, would find deeply alien. Now let's talk about what your daily life actually looks like on the surface. You cannot walk outside without a spacesuit. The Martian atmosphere, while it exists, is completely unbreathable, 95% carbon dioxide, with trace amounts of other gases and almost no oxygen. The pressure is so low that your blood would begin to boil if you were exposed to it without a pressure suit. The temperature swings are extreme. At the equator, a summer day might reach a pleasant 15 degrees Celsius at noon, but plunge to -70 degrees Celsius overnight. A suit failure on the surface would be rapidly fatal, so every time you step outside, you go through an airlock, you suit up, you check your systems, you confirm your oxygen supply, and only then do you step out onto the surface of another world. The suits being designed for Mars missions are a generation beyond the suits Apollo astronauts wore on the Moon. Those suits, while remarkable for their era, were stiff, bulky, and limited mobility severely, famously making it difficult to bend down and pick something up from the ground. Mars suits need to be more flexible, more durable, since Mars missions will involve far more surface time than any Apollo mission, and equipped with more sophisticated life support systems for longer excursions. NASA's XEMU suit, the Exploration Extravehicular Mobility Unit, and SpaceX's Starship suit represent two different approaches to this challenge, each with different design philosophies. Getting the suit right is not a minor detail. The suit is your personal spacecraft. It is the only thing standing between you and an environment that will kill you in seconds. Inside the habitat, life is a study in carefully managed scarcity. Every resource is precious. Water is recycled with extraordinary efficiency. The life support systems on the International Space Station already recover about 93% of the water from astronaut urine, sweat, and exhaled moisture. Mars mission systems will need to push that even higher. 99% recovery. Water that is lost cannot easily be replaced, at least not in the early stages of a mission, before in situ water extraction from the Martian soil or subsurface becomes operational. Food, in early missions, will be entirely brought from Earth. The caloric demands of working in a spacesuit, maintaining a habitat, conducting science, and managing a high-stress environment are significant. Astronauts in demanding conditions can require upward of 3,000 calories per day, storing, preserving, and preparing food for a crew of 4 to 6 people for a mission that might last 500 days or more on the surface represents a substantial logistics challenge. Longer term, growing food on Mars is not just desirable, it is probably necessary for any permanent settlement. Mars has some of what plants need: carbon dioxide in abundance, sunlight, albeit weaker than on Earth, soil minerals, though Martian regolith, the loose surface material, contains perchlorates, toxic chemical compounds that would need to be processed out before it could support plant growth. Water ice exists at the poles and in subsurface deposits. Researchers are actively studying how to create pressurized growing modules, essentially greenhouses, that could produce food crops on the Martian surface. NASA's work on plant growth in space, conducted aboard the International Space Station, has already demonstrated that several crops, lettuce, radishes, chile peppers, and others, can be grown successfully in microgravity. Mars, with its reduced gravity and manageable pressure inside a habitat, may actually be more conducive to plant growth than the ISS. The psychological value of growing and eating fresh food on a long surface mission is also significant. Astronauts consistently describe access to fresh food as one of the most meaningful quality of life factors on long missions. Let's talk about power, because everything, life support, heating, lighting, equipment, communication, depends on power. There are two main approaches to power generation on Mars that are seriously considered for crewed missions. The first is solar. Mars receives less solar energy than Earth, and dust storms can dramatically reduce panel efficiency for weeks or months at a time. But solar technology has advanced enormously. Modern high-efficiency panels produce far more power per square meter than panels of even a decade ago. For some mission architectures and landing sites, solar remains a viable primary power source. The second is nuclear. Specifically, small nuclear fission reactors pack reliable power sources that produce electricity regardless of sunlight, dust, or weather. NASA and the Department of Energy have been developing a system called kilopower, a small nuclear reactor designed for use on planetary surfaces. A scaled-up version called Krusty, kilopower reactor, using Stirling technology, has been tested successfully on Earth. These reactors could provide tens of kilowatts of reliable electrical power, enough to support a small crewed habitat and its associated systems. For a permanent settlement, nuclear power is almost certainly part of the answer. It provides the baseline power that solar simply cannot guarantee in all conditions, and on a world where a dust storm can last for months and cover the entire planet, having a power source that doesn't depend on the sun could literally be the difference between life and death. Now, let's talk about something that almost never comes up in casual discussions of Mars missions, but that I find endlessly fascinating: communication. You are on Mars. Your family is on Earth. You want to send a message. You record it, a video, a voice message, a text. You hit send, and then you wait. Depending on where Earth and Mars are in their respective orbits, the one-way signal delay, the time for your message to travel from Mars to Earth at the speed of light, ranges from about 3 minutes when the planets are at their closest to about 22 minutes when they are on opposite sides of the Sun. And during solar conjunction, when the Sun is directly between Earth and Mars, communications can be disrupted or blacked out entirely for weeks. So a real-time conversation is impossible. You send a message. You wait at minimum 6 minutes for a round trip, or up to 44 minutes. Your family records a reply. You watch it hours later. Every interaction with anyone on Earth is asynchronous, delayed. Every piece of news from home arrives not fresh but old, already happened, already resolved or worsened, without your knowledge. Significant events in the lives of people you love, illnesses, births, deaths, you find out about with a delay of many minutes to nearly an hour. Psychologists studying astronaut mental health flag this communication delay as one of the most emotionally challenging aspects of a Mars mission. On the International Space Station, astronauts can call home in real time. They can video chat with their children at bedtime. That connection, immediate, responsive, warm, is a significant psychological anchor. On Mars, that anchor is gone, replaced by something more like letters exchanged between a sailor on a long voyage and loved ones at home, meaningful but delayed, disconnected from the flow of daily life in a way that can breed a particular kind of loneliness that has no easy remedy. Space agencies are studying how to help crews cope with this. Video libraries from family members, pre-recorded messages to be opened on birthdays, anniversaries, difficult days, AI companions that can provide some form of conversational interaction, crew relationship management, and conflict resolution protocols. The inner life of a Mars crew will need as much careful design and attention as the engineering systems that keep them alive. But let's not lose sight of the other dimension of life on Mars, the extraordinary dimension. Every single day on the surface would be a day of unprecedented discovery. Every rock you pick up might be a rock that has never been touched by an intelligent hand. Every ridge you climb might reveal a valley no eye has ever seen. Every soil sample you analyze might contain chemical signatures that no instrument has yet detected. The science available to a crew on the Martian surface, armed with the judgment, the intuition, the adaptability, and the physical dexterity of human beings, is staggering in its potential, the geology alone. Mars preserves a record of planetary history going back over 4 billion years, far older and more complete than anything accessible on Earth, whose active geology constantly recycles and destroys old rock. Reading that record could tell us about the early solar system, the conditions that led to life on Earth, the nature of planetary magnetic fields, and their relationship to atmospheric retention, and dozens of other profound questions. And then there's the biology question. If Mars ever had life, and the evidence for habitable conditions in its past is genuinely strong, some trace of it might still exist, in fossilized form in ancient rock, in chemical signatures in the soil, or most astonishingly of all, in living form in subsurface environments. The discovery of even a single unambiguous microbial fossil on Mars would be the most significant scientific finding in human history. It would confirm that life is not a once-in-a-universe miracle but a recurring phenomenon, something that arises wherever conditions allow. That discovery, if it comes, might come during the first crewed mission. It might come when a geologist in a spacesuit chips open the right rock at the right time and sees something that no robot algorithm was programmed to recognize. Now let's turn to the return journey, because this is the part that people often skip over in their excitement about getting to Mars, and it matters enormously. Getting home from Mars is in some ways harder than getting there. The first challenge is timing again. Just as the trip from Earth to Mars requires a specific planetary alignment, the return trip also requires waiting for the right launch window. And on Mars, that window also comes roughly every 26 months. So a crew that lands on Mars is not going to turn around and come home a few weeks later. They are there for the long haul, typically 500 days or more on the surface, waiting for Earth and Mars to realign for the return journey. 500 days on the surface, added to 7 months going and 7 months coming back. Total mission duration for a round trip to Mars is likely to be somewhere around 2.5 to 3 years. 900 days or more from Earth departure to Earth return. That is not a short trip. That is an expedition of a scale that dwarfs anything in modern exploration experience. The longest continuous stay by a single individual in space is currently held by Russian cosmonaut Oleg Kononenko, who surpassed the record with a mission lasting over 374 days on the International Space Station. A Mars mission crew would need to more than double that, and do it in far more isolated, far more demanding conditions, with far less ability to receive emergency assistance. The return launch from Mars presents its own engineering challenges. The Martian gravity well, while weaker than Earth's, still requires significant energy to escape. A return vehicle needs to carry enough propellant to lift off from the surface, achieve Martian orbit, and then perform the burn that sends it on a trajectory back toward Earth. This is why the in-situ propellant production concept we discussed earlier is so critically important. Carrying all that return propellant from Earth would make the mission mass requirement staggering. Producing it on Mars using the Martian atmosphere and any available water ice, is the only practical solution for making the mission architecture economically and logistically feasible. The plan, in most serious mission architectures, is to send the return vehicle and the propellant production system to Mars in advance, uncrewed. Let the propellant system spend a year or more filling the return vehicle's tanks. Confirm remotely that the tanks are full and the vehicle is ready, and only then, only when you know your crew has a way home, do you launch the crew. This is how you manage the risk. You don't send people to Mars and figure out the return trip when they get there. You have the exit door open and waiting before anyone walks through the entrance. The journey home will, in many ways, mirror the journey out. Another 6 to 7 months in transit. Another extended period of microgravity, radiation exposure, isolation, the same physical challenges, bone loss, muscle atrophy, cardiovascular deconditioning, building on top of whatever impact the surface stay has had, and then, at the end, re-entry into Earth's atmosphere, which presents its own challenges. After 2.5 to 3 years of reduced or zero gravity, the crew will be returning to the full gravitational pull of Earth. 1 full G, far greater than anything they have experienced since leaving. Astronauts returning from 6-month ISS missions often cannot walk unassisted immediately after landing. They are carried out of their Soyuz capsules and sit in chairs while medical teams check their vitals. Their cardiovascular systems need time to readjust. Their muscles and bones, despite months of exercise countermeasures, have weakened. A Mars crew returning after 3 times that duration in space will face a far more intense readaptation challenge. The rehabilitation process will be extensive, potentially taking a year or more of intensive physical therapy and medical monitoring before full recovery. Some changes, particularly to bone density and possibly vision, may never fully reverse. These are people who will have given something of themselves that cannot be taken back. The physical toll of a Mars mission is permanent in ways that we are still working to fully understand, and they will have done it anyway. There is something in that choice that echoes through human history. The Polynesian navigators who set out across the Pacific in outrigger canoes, guided by stars and wave patterns and the flight of birds, knowing they might never find land. The European explorers who sailed beyond the mapped edges of the world toward possibilities that were terrifying precisely because they were unknown. The test pilots of the early jet age who climbed into aircraft that had never been flown to speeds and altitudes that had never been attempted, knowing that the physics books were still being written. Every generation has had its horizon. Every generation has had its people who walked toward it when others held back. The Mars astronauts will be those people for our generation. And for the generations that come after, here's what I want you to carry with you into the second half of our journey through this story. We started with a simple question: how long would it really take to reach Mars? And that question has opened into something so much larger. We've traveled through orbital mechanics and radiation physics, through bone loss and 7 minutes of terror, through the arguments for exploration and the honest reckoning with its costs, through the butterscotch sky and the profound silence and the communication delays and the science waiting to be done. And we haven't even gotten to what comes after the first mission, the larger story, the permanent settlement, the question of what Mars does to human beings, not just physically, but culturally, spiritually, philosophically. What it means for a child to be born on Mars, to have Mars as their home, Earth as a distant light in the sky, a place their parents came from but they have never seen. What does it mean to be Martian? That question, and the extraordinary scientific and ethical territory surrounding it, is what the next part is built around. And I promise you, it goes places that will make you think about what it means to be human in a way you haven't before. Let's start with a birth, Not a metaphorical one, a literal one. Imagine, somewhere in the mid-21st century, perhaps 50 or 60 years from now, a child is born on Mars. The first human being in all of history whose first breath is drawn not from Earth's air, but from the carefully recycled, precisely maintained atmosphere of a pressurized habitat on another world. This child opens their eyes for the first time and sees the interior of a habitat, curved walls, soft artificial lighting calibrated to approximate the wavelengths of sunlight that human biology evolved under, the faces of their parents, people who made an extraordinary choice to leave Earth permanently to build something new on a world that was not built for them. This child will grow up knowing Mars as home, not as a destination, not as an adventure. Home. They will look up through a reinforced viewport at a butterscotch sky and feel the same pull of familiarity that you feel when you look at a blue one. They will walk in 38% gravity and find Earth's full gravity, if they ever go there, crushing and strange. Their bones and muscles and cardiovascular system will develop in a lower gravitational field, potentially producing physiological differences from Earth-born humans that we can currently only theorize about. This child, this first Martian, will be the beginning of something that has no precedent in the 4-billion-year history of life on Earth. A new branch of humanity. Let's think carefully about what that means, because it is one of the most profound and underexplored aspects of the whole Mars conversation, and it raises questions that sit right at the intersection of science, philosophy, ethics, and what it fundamentally means to be human. First, the biology. Human beings evolved over millions of years under specific conditions, 1 full G of gravity, a specific atmospheric pressure, a particular mix of gases, a particular radiation environment modulated by our magnetic field and atmosphere, a specific relationship with sunlight, our circadian rhythms, our vitamin D synthesis, our sleep-wake cycles, our mood regulation, all calibrated to Earth's 24-hour day and the particular spectrum of sunlight that reaches our surface. Mars has a day, called a sol, that lasts 24 hours, 39 minutes and 35 seconds, remarkably close to Earth's day. This is actually one of the most fortuitous coincidences in Mars mission planning. Researchers and engineers who operate the Curiosity and Perseverance rovers have had to synchronize their work schedules to Martian sol time, shifting by 39 minutes every single day, and have described the experience as deeply disorienting, like permanent jet lag. For the first Martian settlers, the sol length might actually be easier to adapt to than it is for Earth-based mission controllers, since their entire environment would be synchronized to Mars time. But gravity is a different matter. 38% of Earth's gravity, sustained over a lifetime, would almost certainly produce measurable changes in human physiology. Children born and raised on Mars might develop differently, taller perhaps, since gravity is a significant factor in how the skeletal system develops. Their hearts might develop differently, since the cardiovascular demands of pumping blood against a weaker gravitational pull are different. Their muscle mass and bone density might stabilize at levels that are perfectly adequate for Mars, but would leave them physically unable to tolerate Earth's gravity without serious health consequences. After a generation or two, Martian-born humans might literally not be able to return to Earth, not for political reasons, not for cultural reasons, but because their bodies, shaped by a lifetime of lower gravity, could not withstand the physical demands of 1 full G at that point, and this is where it gets philosophically dizzying. Are they still human? In the biological sense, almost certainly yes. In the cultural and experiential sense, they will be something genuinely new, people for whom Earth is a story their grandparents told, a blue dot in the Martian night sky, a place of mythology and origin rather than lived experience. This raises what philosophers and anthropologists are already beginning to call the question of Martian identity. What does it mean to be from Mars? What language do you speak? The language your parents brought from Earth, or something that evolves over generations of isolation and shared experience into something new? What stories do you tell? What holidays do you celebrate? What is sacred to you? Human cultures are shaped profoundly by their physical environments. The civilizations that arose in river valleys developed differently from those in deserts or forests or archipelagos. The rhythms of agriculture, the demands of survival, the resources available, the threats faced, all of these shape culture in ways so deep they become invisible to the people living inside them. Martian culture, if Mars is ever settled permanently, will be shaped by the Martian environment in ways we cannot fully predict, by the constant awareness of danger, the suit that must always be checked, the airlock that must always be respected, the life support system that must always be maintained, by the scarcity of certain resources and the abundance of others, by the view from the habitat window, by the particular quality of Martian light, by the silence. There is a concept in anthropology called island biogeography, the study of how isolated populations develop distinct characteristics over time, diverging from the populations they originated from. Mars would be the ultimate island, the most isolated human population in history, and over generations, that isolation would produce divergence, biological, cultural, linguistic, psychological, that might eventually be profound enough to make Martians feel genuinely alien to Earth humans, not alien in a science fiction sense, but different in the deep, unsettling way that any traveler feels when they encounter a culture that has evolved under entirely different pressures from their own. Now let's get into territory that is genuinely controversial, because no serious discussion of long-term Mars settlement can avoid it. Terraforming, the word comes from the Latin for Earth, terra. Terraforming Mars means transforming its environment to make it more Earth-like, thickening the atmosphere, warming the planet, introducing liquid water to the surface. Eventually, over timescales of centuries or millennia, creating conditions where human beings could walk on the surface without a spacesuit. The concept is not new. Science fiction writers have been exploring it for decades. Kim Stanley Robinson's Mars trilogy, Red Mars, Green Mars, Blue Mars, remains one of the most detailed and thoughtful explorations of what Martian terraforming might actually look like over the course of 3 centuries. It's a masterwork of scientific imagination, and I genuinely recommend it to anyone captivated by this topic. But is terraforming actually possible, and should we do it even if it is? Let's start with the science. Mars has several things working against it as a candidate for terraforming. The biggest is its weak magnetic field, or more precisely, the near-complete absence of a global magnetic field. Mars lost its magnetic field billions of years ago when its core cooled and solidified, stopping the churning that generates a planetary magnetic field. Without that field, the solar wind gradually strips away atmosphere, which is in fact the leading hypothesis for how Mars lost most of its original thick atmosphere in the first place. So if you thicken the Martian atmosphere, which is theoretically possible using various methods including releasing greenhouse gases, redirecting asteroids containing volatile compounds, or deploying giant space mirrors to warm the planet, the solar wind will gradually erode it again over geological timescales. You would need either to regenerate the magnetic field somehow, or to continuously replenish the atmosphere, or to accept that your terraformed Mars has a finite lifespan on a geological timescale. Generating a planetary magnetic field is, with current or foreseeable technology, essentially impossible. Some researchers have proposed placing a magnetic shield, an artificial magnetosphere generator, at the Mars L1 point, a gravitationally stable position between Mars and the Sun, where it could deflect solar wind before it reaches the planet. This has actually been seriously studied by NASA scientists. It is extraordinarily ambitious, but does not violate any known laws of physics. The timescale for any terraforming effort is humbling. Even the most optimistic scenarios envision centuries of effort before the Martian surface becomes broadly habitable without pressure suits. More conservative estimates run to thousands of years. This is not a project that any individual, company, or even nation undertakes and completes. It is a multi-generational commitment of a scale that makes our largest current civilizational projects, the great cathedrals of medieval Europe, the construction of the pyramids, look like weekend hobbies. But here is where the ethics become genuinely thorny, and I want to sit with this because I think it deserves serious reflection rather than a quick dismissal in either direction. If Mars harbors life, even microbial life, hidden in subsurface environments, then terraforming would mean destroying or drastically altering the only other living ecosystem we have ever found. The ethical weight of that is staggering. We would be making a unilateral decision to override a 4-billion-year-old biological history on another world for our own convenience. This is not a hypothetical that can be brushed aside. The same scientific interest that drives us to go to Mars to search for life should give us profound pause about the prospect of sterilizing or transforming whatever we find there. The debate within the scientific and philosophical community is real and ongoing. One position holds that any Martian life discovered would, by virtue of its existence, make Mars off-limits for terraforming, at least until we understand it thoroughly and find ways to protect it. Another position argues that microbial life on Mars, if it exists, is likely so hardy and so deeply subsurface that surface terraforming would not meaningfully threaten it. A third position raises the question of moral status. Are microbes on Mars, if they exist, owed the same ethical consideration as complex animals? Is preventing their extinction worth sacrificing the possibility of making Mars habitable for humans? These are not questions with easy answers. They are exactly the kinds of questions that humanity needs to begin wrestling with seriously. Before we have boots on the ground and the decisions become irreversible, Carl Sagan himself expressed this tension. He was deeply committed to human space exploration, to the idea of making humanity multiplanetary, and yet he also argued passionately that if Mars has life, that life has rights, that a living Mars is more valuable to science and to the universe than a terraformed Mars. It is a tension without a clean resolution. And I think sitting with that tension, rather than rushing to resolve it, is the honest and intellectually responsible position. Let's pull back even further now, because there is a layer to this whole conversation that we haven't explicitly named yet. One that gives everything we've been discussing a different kind of weight and meaning. We are not the first generation to ask whether life exists beyond Earth. Human beings have been gazing at the stars and wondering if they harbor other minds, other lives, other stories, for as long as we have records of human thought. Ancient philosophers speculated about the plurality of worlds. Giordano Bruno was burned at the stake in 1600, partly for insisting that the stars were other suns with other planets and possibly other inhabitants. The question of life beyond Earth is one of the oldest and deepest questions in human intellectual history, and we are the first generation that has a realistic chance of answering it. Not for the stars, those are still incomprehensibly far away, and the challenges of interstellar travel, as we explore in the video about interstellar journeys, are in a different category entirely from Mars. But for Mars, our nearest, potentially life-bearing neighbor, we are within reach. Not metaphorically, literally. Within the lifetime of many people watching this video, human beings will set foot on Mars and conduct the most consequential biological investigation in history. The Mars Sample Return mission, bringing those rock cores that Perseverance has been collecting back to Earth for analysis in the best laboratories our species has ever built, could potentially answer the question of ancient Martian life within this decade. Scientists using instruments far more sensitive than anything that can be sent to Mars directly will be able to search those samples for biosignatures at a molecular level. If they find something, even the faintest chemical whisper of ancient biology, the world will never look at the night sky the same way again. And if they find nothing, if those ancient rocks are completely, unambiguously sterile, that too is a profound result. It would suggest that life on Earth is perhaps genuinely rare, that the emergence of biology from chemistry is not automatic even given the right conditions. And that finding makes us, you, me, every living thing on this planet, something almost incomprehensibly precious in a vast and mostly empty universe. Either answer changes everything. There is another possibility that occupies a fascinating corner of astrobiology and that occasionally surfaces in serious scientific discussions, though it remains highly speculative: panspermia. The hypothesis that life can travel between worlds, carried on meteorites ejected by asteroid impacts, surviving the journey through space in a dormant state and potentially seeding new planets. We know that material travels between Mars and Earth. Hundreds of Martian meteorites have been found on Earth, rocks blasted off the Martian surface by ancient asteroid impacts, drifting through space for millions of years, eventually captured by Earth's gravity and landing on our surface. Scientists have studied these meteorites extensively. One of them, designated ALH 84001, found in Antarctica in 1984, caused a global scientific sensation in 1996 when NASA researchers announced they had found what appeared to be microscopic structures resembling fossilized bacteria inside it. The subsequent scientific debate was intense and remains unresolved. The consensus today is that the structures in ALH 84001 are probably not biological in origin, that they can be explained by non-biological chemistry. But the debate sharpened the scientific community's thinking about what evidence of past Martian life would actually need to look like to be convincing. The panspermia hypothesis raises a genuinely mind-bending possibility. What if life on Earth and life on Mars, if it exists, share a common ancestor? What if, 4 billion years ago, a meteorite impact on one world seeded the other? What if we and whatever might be living in Martian subsurface aquifers are, in some deep biological sense, related? If that is true, if Earth life and Martian life share common ancestry, then finding life on Mars would not be the discovery of truly independent life. It would be the discovery of a cousin, still extraordinary, still revolutionary, but different in its implications for the frequency of life in the universe. Distinguishing between these possibilities, independent origin versus panspermia, would require detailed molecular analysis of any Martian life found. Does it use DNA, the same genetic code, the same amino acids? The answers would tell us something fundamental about how life works across worlds. Now I want to bring this back to something personal, something that connects all of this cosmic scale to the experience of a single human life. Think about the arc of exploration that humanity has traveled just in the last few hundred years. In the early 1500s, European explorers were discovering that the world was larger than their maps suggested. By the 1600s, the telescope had revealed that the universe was larger than anyone had imagined, that the stars were not points of light on a celestial sphere, but distant suns incomprehensibly far away. By the 19th century, we had circumnavigated the globe, charted its continents, reached its poles. By the 20th century, we had broken the sound barrier, reached orbit, walked on the moon, and now, in the 21st century, we are planning, seriously, concretely planning, to send human beings to another planet. Each generation has expanded the boundary of the known. Each generation has faced its own version of the people who said it couldn't be done, wasn't worth doing, was too dangerous, too expensive, too ambitious, and each generation has produced people who did it anyway. There is a continuity to this story, a thread that runs from the first human who looked up at the night sky and wondered, to the engineers building Starship in Texas and the scientists analyzing Martian rock samples in Houston and the astronauts training for lunar missions in preparation for Mars. We are all part of that thread. Even you watching this video, asking these questions, feeling that pull of curiosity and wonder, you are part of it. The universe creates curious minds. Curious minds ask questions. Questions drive exploration. Exploration expands what we know, and expanding what we know reveals how much more there is to wonder about. It is a beautiful, endless, self-renewing cycle, and it has been going on, in one form or another, for as long as there have been human beings. Let me leave you with a thought that I find genuinely moving. When the first human being lands on Mars and takes that historic first step, whenever it happens, whoever it is, they will carry with them the accumulated knowledge and curiosity and determination of every scientist, every engineer, every explorer, every dreamer who ever looked at that reddish dot in the sky and wondered. They will carry Isaac Newton and Johannes Kepler, whose laws of motion and planetary movement make orbital mechanics possible. They will carry Robert Goddard, who launched the first liquid-fueled rocket in a field in Massachusetts in 1926, while people called him a fool for believing it could work. They will carry the Soviet engineers of the space race, and the NASA teams of Apollo, and the astronomers who mapped Mars from afar for generations before anyone could go there. They will carry Sagan's pale blue dot and Hubble's deep field, and every photograph ever taken of the cosmos that made a child somewhere look up and feel that irresistible pull. They will carry you. Because the curiosity that brought you to this video, the willingness to ask big questions and sit with complex answers and feel the weight and the wonder of what our species is attempting, is the same force that drives exploration forward. It is the same force that built the telescopes and the rockets and the rovers. It begins with someone, somewhere, asking a question, questions like, how long would it really take to reach Mars? We are approaching the final sections of this journey, and there is so much still to explore. We haven't yet talked about the technologies that could make the trip not just possible, but relatively fast. The cutting edge of propulsion science that could compress 7 months into weeks. We haven't talked about the international and commercial landscape of the new space race in detail. Who is actually going, when, and what their plans look like up close. We haven't talked about the moon as the critical training ground it needs to be, and what the Artemis program has accomplished and still needs to achieve. And we haven't done the final accounting, the complete, honest answer to the question this video started with. Not just the physics answer, the full answer, the one that takes into account everything we've explored together. If you are still watching, make sure to subscribe and give this video a like. Your support means the world to me. Takes 1 second but makes all the difference. Let's talk about speed. Not the polite, carefully managed speed of a Hohmann Transfer Orbit, coasting through the inner solar system on a graceful 7-month arc. Not the speed of chemical rockets burning for a few minutes and then going silent for the rest of the journey. Let's talk about the kind of speed that would fundamentally change what a Mars mission looks like. The kind of speed that would compress months into weeks. The kind of speed that would make the radiation problem dramatically more manageable. The psychological isolation problem dramatically more tolerable, and the whole enterprise of sending human beings to Mars is dramatically more survivable. Because that kind of speed is not science fiction, it is science in progress. And some of the most brilliant minds in aerospace engineering are working on it right now, in laboratories, in test facilities, in the pages of peer-reviewed journals that most people never read, but that are quietly mapping the future of human spaceflight. Let's walk through what is actually on the table. We already touched on nuclear thermal propulsion in an earlier section, the technology that uses a nuclear reactor to superheat propellant and expel it at far higher velocities than chemical combustion can achieve, roughly doubling the efficiency of the engine. That alone could cut the Mars transit time from 7 months to somewhere between 3 and 4 months. Meaningful, important, but not transformative in the deepest sense. To get truly transformative, to talk about weeks rather than months, you need to go further. You need nuclear pulse propulsion, or nuclear electric propulsion, or something even more exotic. Let's start with nuclear electric propulsion. This is a step beyond nuclear thermal. Instead of using a nuclear reactor to heat propellant directly, you use it to generate electricity, large amounts of electricity, which then powers an ion drive or a similar electric propulsion system. Remember those ion drives we talked about earlier? The ones that generate tiny thrust but extraordinary fuel efficiency and can run continuously for months or years. Now imagine powering them not with the limited solar panels that constrain current ion drive spacecraft, but with a compact nuclear reactor that produces hundreds of kilowatts or even megawatts of electrical power, regardless of distance from the sun. Suddenly, that gentle but persistent thrust becomes far more capable. A nuclear electric propulsion system could accelerate a crewed spacecraft to much higher velocities over a sustained period, and then flip around and decelerate at the other end, bringing the crew to Mars in a controlled, relatively comfortable trajectory. Depending on the power level and the specific design, some studies suggest nuclear electric propulsion could reduce Mars transit times to somewhere between 45 and 90 days, 6 to 13 weeks, not months, weeks. NASA and the Department of Energy have been working on nuclear electric propulsion concepts for decades under various program names. The technology challenges are real: managing the heat generated by the reactor, building power conversion systems that work reliably in deep space for extended periods, developing electric thrusters capable of handling the power levels involved, but none of them represent fundamental physics barriers. They are engineering problems, hard ones, but tractable ones. Now let's talk about something even more ambitious, something that occupies the frontier between current engineering and the next generation of possibility: fusion propulsion. Nuclear fission, splitting heavy atoms apart, is what powers current nuclear reactor concepts for space. Nuclear fusion, forcing light atoms together, is the process that powers the sun. It releases far more energy per unit of fuel than fission, produces far less radioactive waste, and uses fuel, primarily isotopes of hydrogen, that is relatively abundant. The challenge, of course, is that controlled nuclear fusion has been the most elusive goal in energy research for the last 70 years. The joke in the fusion community has long been that commercial fusion power is always 30 years away, and has been for decades. But something genuinely interesting has happened in the last few years. Private fusion companies, funded by billions of dollars of investment from some of the most sophisticated investors in the world, have made real documented progress. Commonwealth Fusion Systems, a spin-out from MIT, achieved record magnetic field strengths with their high-temperature superconducting magnets in 2021, a genuine milestone on the path to a compact fusion reactor. TA Technologies, Helion Energy, General Fusion. These are companies with serious engineering teams making measurable progress toward a goal that once seemed perpetually out of reach. If, and it remains a significant if, compact fusion reactors become a reality in the coming decades, the implications for space propulsion are extraordinary. A fusion rocket could theoretically achieve specific impulses orders of magnitude beyond anything possible with fission or chemical propulsion. Transit times to Mars of weeks, even days, become at least theoretically plausible depending on the specific design and power levels achieved. We are not there yet, but we are moving in that direction at a pace that would have seemed implausible even 15 years ago. The fusion horizon, which once seemed perpetually fixed at 30 years away, may genuinely be getting closer. Then there are the concepts that exist right now primarily as equations and simulations, grounded in real physics but requiring engineering capabilities that are decades or more away. Solar sails are actually the most near-term of these. The concept is elegant. Use the pressure of sunlight itself to propel a spacecraft the way a sailing ship uses wind. Light exerts a tiny but real pressure on any surface it strikes. This is called radiation pressure, and it is a well-documented physical phenomenon. A sufficiently large, sufficiently thin, sufficiently reflective sail could capture enough of this pressure to gradually accelerate a spacecraft. The Japanese space agency JAXA demonstrated the first successful solar sail deployment in space with their Icaros spacecraft in 2010, a genuine landmark in space technology. The Planetary Society has also successfully deployed and operated small solar sail spacecraft. These are real, working systems. The limitation of solar sails for Mars missions is that solar pressure is relatively gentle and it weakens with distance from the Sun. Accelerating a large, heavy crewed spacecraft to useful interplanetary velocities using sunlight alone would require sails of impractical size, kilometers across, and would still take a very long time. But here's where it gets interesting. What if you didn't use sunlight? What if you used a laser? Laser propulsion, sometimes called directed energy propulsion, would use a powerful laser array on Earth or in orbit to illuminate a sail at much higher intensities than sunlight provides, accelerating a spacecraft far more rapidly. Breakthrough Starship, a research initiative announced in 2016 and backed by physicist Stephen Hawking and investor Yuri Milner, proposed using this concept to accelerate tiny probes, gram-scale spacecraft, to a significant fraction of the speed of light for interstellar missions. The physics are real. The engineering challenges are extraordinary. For crewed Mars missions, laser propulsion at the scale needed would require power levels that are currently well beyond any existing infrastructure. But as a long-term concept, decades out, it represents a genuinely interesting direction. And then there is the idea that sits at the very edge of what current physics can contemplate without moving into speculation. The Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre published a paper describing a solution to Einstein's equations of general relativity that would allow faster-than-light travel, not by moving a spacecraft through space faster than light, which relativity forbids, but by contracting space-time in front of the spacecraft and expanding it behind, so that the spacecraft effectively surfs a wave of space-time without ever locally exceeding the speed of light. The concept is mathematically legitimate. It does not violate general relativity, at least as currently understood. The problems are engineering ones of a magnitude that makes everything else we've discussed look trivial. The original calculations suggested that creating the necessary space-time distortion would require an amount of exotic matter with negative energy density, equivalent to the mass energy of a planet the size of Jupiter. Subsequent refinements have brought those estimates down somewhat, but the energy requirements remain staggering beyond any conceivable current or near-future technology. More importantly, the existence of the specific type of exotic matter required has never been demonstrated. It may not exist. The Alcubierre drive may be a mathematical curiosity rather than a practical possibility. But here's why I mention it. Not because warp drives are coming, but because the fact that our understanding of physics allows us to even conceive of mechanisms like this, that general relativity is rich enough to contain solutions that permit space-time manipulation, is a reminder of how much we still do not know about the deep structure of the universe. Physics has surprised us before. Quantum mechanics was unimaginable to 19th century physicists. General relativity itself would have seemed like fantasy to Newton. The history of physics is a history of profound surprises. What surprises might the next century of physics hold? We genuinely do not know. And that uncertainty, that vast, exciting space of the unknown, is one of the most beautiful aspects of being alive at this moment in history. All right, let's bring this back to Earth, or rather, to the launch pad, because all of this visionary propulsion science lives in the future. The question that space agencies and companies are grappling with right now, in the immediate term, is more concrete. Which technologies can actually be ready in time for a crewed Mars mission in the 2030s? And what does the competitive landscape of the new space race actually look like? Let's map it out honestly. The United States remains the leader in Mars surface operations by a significant margin. 4 out of 4 attempted Mars rover landings by NASA have been successful, a record no other nation comes close to matching. The technical expertise accumulated through decades of Mars missions is deep and institutional. The Jet Propulsion Laboratory in Pasadena, California remains one of the most remarkable engineering organizations on the planet, but NASA operates within the constraints of the American political system, subject to budget cycles, changes in administration, and the competing priorities of a democratic government. The Artemis program, which aims to return Americans to the moon, has faced significant delays and cost overruns. The Space Launch System, the massive rocket at the center of NASA's human spaceflight program, has been extraordinarily expensive to develop and operates at a very low flight rate compared to commercial alternatives. SpaceX represents something genuinely new in the landscape, a private company, but one with explicitly interplanetary ambitions, developing technology at a pace and cost structure that no government program has matched. Starship, if it achieves its design goals of full and rapid reusability, would reduce the cost of getting mass to orbit by an order of magnitude compared to current systems. SpaceX has explicitly stated that the purpose of Starship is to enable human colonization of Mars. This is not marketing language, it is the stated engineering goal driving the design of the vehicle. The relationship between NASA and SpaceX on the path to Mars is complex. SpaceX is both a NASA contractor, building the lunar lander for the Artemis program, and an independent actor with its own Mars timeline that may not align with NASA's. Whether the first humans on Mars arrive on a NASA mission, a SpaceX mission, or some collaboration between the two is genuinely uncertain. China's space program has demonstrated extraordinary capability and ambition in recent years. The Tianwen-1 Mars mission in 2021 deployed both an orbiter and the Zhurong rover, making China only the second nation to successfully operate a rover on the Martian surface after the United States. The Chang'e lunar program has conducted multiple successful lunar landings and sample returns. The Tiangong space station is operational and supporting crewed missions. China's official space roadmap includes crewed lunar missions in the 2030s and has referenced Mars crewed missions in general terms, though specific timelines for crewed Mars exploration have not been formally announced. The pace and secrecy of Chinese space program development makes it difficult to assess from the outside with precision, but the trajectory is clearly upward and the capability is clearly growing. The geopolitical dimension of this matters. If the race to Mars takes on the character of a competition between the United States and China, similar to the Apollo-era race with the Soviet Union, it could actually accelerate timelines as political competition historically has. The Apollo program reached the Moon in 8 years partly because the Soviet threat made speed a national priority. A similar dynamic in the 21st century Mars race could compress timelines significantly. The European Space Agency has been a sophisticated partner in Mars exploration. The Mars Express orbiter has been operating since 2003, the longest continuously operating spacecraft at Mars. ESA's ExoMars program, in collaboration originally with Russia and now being restructured in the aftermath of geopolitical changes following Russia's invasion of Ukraine, aims to place a rover called Rosalind Franklin on the Martian surface. ESA has not articulated a timeline for crewed Mars missions independently, but participates in collaborative discussions with NASA and other partners. India's space agency ISRO placed its first Mars orbiter, Mangalyaan, successfully into Martian orbit in 2014 on the agency's first attempt, making India only the 4th space agency to reach Mars and the first Asian nation to do so. The cost of the mission was remarkably low by interplanetary standards, less than $74 million, making it one of the most cost-effective interplanetary missions ever flown. ISRO is developing its capabilities steadily and has announced ambitions for deep space exploration, though crewed Mars missions are not yet part of its near-term planning. So here is the honest, evidence-based answer to the question of when. A robotic Mars sample return, bringing Martian rocks to Earth for analysis, is the most scientifically urgent near-term milestone. If the mission proceeds as currently planned, it could happen in the mid to late 2030s, though budget pressures have created uncertainty. A crewed Mars mission in the early 2030s is within the range of possibility, but only if SpaceX's Starship development continues at its current pace and achieves its reusability goals, if nuclear propulsion development reaches flight readiness, and if political will and funding hold. This is an optimistic scenario, not a conservative one. A more conservative but still genuinely hopeful timeline puts the first crewed Mars landing in the late 2030s to early 2040s. This assumes Artemis successfully establishes a sustained lunar presence, the medical countermeasures for long-duration spaceflight reach adequate effectiveness, and the international or commercial funding structures necessary for a Mars program are assembled. A pessimistic but not impossible scenario pushes the timeline to the 2050s or beyond. If key technologies fail to mature as hoped, if funding collapses, if a major mission accident sets programs back, if geopolitical factors disrupt international cooperation, the range is wide, the uncertainty is real, but across all of these scenarios, the direction is clear. We are going. The question is not whether, the question is when. And the answer is sooner than most people think possible, and later than the most optimistic voices claim. Now, let's do the final accounting that this video has been building toward. How long would it really take to reach Mars? The physics answer: the minimum transit time using current chemical propulsion and optimal planetary alignment is roughly 6 to 7 months. This is the answer that applies to missions like Perseverance and Curiosity. And it would apply to an early crewed mission using similar propulsion technology. The engineering answer: what becomes possible with near-term propulsion advances like nuclear thermal propulsion is roughly 3 to 4 months, a meaningful improvement, achievable within the time frame of a realistic crewed mission program. The medium-term answer: What becomes possible with nuclear electric propulsion and advanced ion drive systems powered by nuclear reactors is roughly 6 to 13 weeks, a transformation that changes not just the travel time, but the medical risk profile of the mission entirely. The long-term answer, what fusion propulsion or other advanced concepts might eventually make possible, could be days to weeks. But this is decades away at minimum, contingent on physics and engineering breakthroughs that are not yet achieved. And the complete answer, the one that accounts for not just transit time, but the full experience of the mission, is this. Getting to Mars takes 7 months of transit, 500 days on the surface, waiting for the right return window, and another 7 months coming home. From Earth departure to Earth return, roughly 900 days, 2.5 years of your life, away from everything and everyone you know, in conditions of isolation and physical demand that have no precedent in human history. That is the real answer. Not just the distance, not just the transit time, the full weight of what the journey means for the human beings who will make it. And here is what strikes me most about that answer. People will still go. When the mission is ready, when the technology is proven, and the medical protocols are in place, and the window opens, there will be people who raise their hands. People who have spent their lives preparing for exactly that moment. People who understand completely what they are signing up for, the radiation, the bone loss, the isolation, the communication delays, the physical toll of the return, and who say yes anyway, because that is who we are. We are the species that crossed oceans in wooden boats. That climbed to the top of the highest mountain on Earth, not because it was strategically necessary, but because it was there. That descended to the deepest point in the ocean. That built the Hubble Space Telescope and pointed it at a patch of seemingly empty sky and found thousands of galaxies that no one knew existed. We are restless, we are curious, we are, at our best, profoundly, irrepressibly drawn toward the unknown. Mars is the next unknown, and we are going, but there's one final dimension of this story that we haven't fully explored yet. One that brings everything full circle, back to the question of what this journey means, not just for the people who make it, but for all of us who watch from Earth. And there's something about the current moment in history, right now, in the mid-21st century, as multiple nations and companies and communities of brilliant people converge on the same goal, that I find deeply moving and want to try to articulate properly. That's where Part 9 takes us. The meaning of it all, the cosmic perspective, the thing that Carl Sagan tried to express and that I want to try to express in my own way, the reason why this matters not just as a technical achievement, but as a statement about what kind of universe we live in and what kind of creatures we are. It is the most important part of this whole conversation. I want to start this section with a number, not a travel time, not a distance, not a temperature or a radiation dose or a propellant mass fraction, a different kind of number entirely, 4 billion years. That is roughly how long life has existed on Earth. 4 billion years of unbroken biological continuity and chain of living organisms, each one passing its genetic instructions to the next, stretching back to the first self-replicating molecules that somehow, in the warm chemistry of an early ocean, crossed the extraordinary threshold from non-living to living. 4 billion years of evolution, of trial and error on a cosmic scale, of extinction and adaptation and diversification, of single cells becoming multicellular organisms, of fish becoming amphibians, becoming reptiles, becoming mammals, becoming primates, becoming us. Every living thing on this planet, every bacterium, every fern, every whale, every eagle, every human being is part of that 4 billion year chain. We are not separate from nature. We are nature in one of its most recent and most astonishing configurations, and in all of those 4 billion years, in all of that vast, rolling, unceasing biological history, Not once has life on Earth intentionally sent itself to another world. Until now, we are the first. In 4 billion years of life on this planet, we are the first generation of living things to look up at another world and say, we are going there, not just to look, not just to send machines, but to go ourselves, to carry life, the same 4 billion year old thread, to a new world for the first time in the history of this planet. Let that land for a moment. Because I think we talk about Mars missions in the language of engineering and politics and timelines and budgets, and in doing so, we sometimes lose sight of the sheer biological and historical enormity of what we are attempting. This is not just an achievement of human civilization. This is an event in the history of life on Earth, an event of magnitude that has not occurred since the first organisms crawled from the sea onto land, or since the first winged creatures took to the sky. Life is about to leave its home planet, for the first time ever. Now let's think about what that means from the perspective of the universe itself. We live in a cosmos that is 13.8 billion years old. A cosmos containing somewhere between 100 billion and 2 trillion galaxies, each one containing hundreds of billions of stars. A cosmos so vast that the light from its most distant observable regions has been traveling toward us since before the Earth existed, and still has not yet had time to reach us. In that cosmos, on a small rocky planet orbiting an unremarkable yellow star in the outer arm of an average spiral galaxy, chemistry became biology 4 billion years ago. Biology became complexity. Complexity became consciousness. And consciousness, after a few 100,000 years of developing language, culture, science, and technology, is now preparing to take its first step beyond the world that created it. When you frame it that way, the question of how long it takes to reach Mars begins to feel almost secondary. The more staggering question is that we are going at all, that the universe has, through the blind and patient process of evolution, produced creatures capable of crossing interplanetary distances and asking questions about their own place in the cosmos. The physicist Freeman Dyson once wrote that the universe is constructed in a way that makes it possible for life and mind to play an increasingly important role in it as time goes on. He called this the universe as a home for life, the observation that the laws of physics seem in various ways conducive to the emergence of complexity. Whether this reflects something deep about the structure of reality, or simply our inevitable bias as living things trying to understand the universe that produced us, remains one of the deepest open questions in philosophy and physics. But here is what we know with certainty. The universe made us. Stars forged the carbon in your body in nuclear reactions billions of years ago, and then scattered it into space when they died. That carbon found its way into a solar nebula that collapsed into the sun and the planets. It became part of the chemistry of early Earth. It became part of the first living cells. It flowed through 4 billion years of biological evolution until it was organized temporarily into the particular arrangement of atoms that is you. Reading this, thinking about Mars, feeling curiosity and wonder, and perhaps a hint of vertigo at the scale of it all, you are the universe becoming aware of itself. Not metaphorically, literally. The atoms in your body are made of the same stuff as the stars. Your consciousness is an emergent property of matter that was forged in stellar nuclear furnaces. When you look up at the night sky and feel wonder, that is the cosmos, through you, experiencing its own existence. And when human beings travel to Mars, they are carrying that awareness, that astonishing, fragile, irreplaceable spark of consciousness to a new world. They are extending the reach of the universe's self-knowledge across interplanetary space. There's nothing small about that. Carl Sagan understood this more deeply than almost anyone. He spent his career trying to communicate not just the facts of astronomy, but the emotional and philosophical weight of what those facts mean for how we understand ourselves and he did it with a clarity and a warmth that still resonates decades after his death. His most famous expression of this perspective came from the photograph known as the pale blue dot, an image of Earth taken by the Voyager 1 spacecraft in 1990 from a distance of roughly 6 billion kilometers as it was leaving the solar system. In the image, Earth appears as a tiny, almost invisible point of light, a mote of dust suspended in a sunbeam, as Sagan described it. He wrote, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." He then added something that I want you to hold carefully. He said, "Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near term, to which our species could migrate." He wrote that in 1994, before Mars mission planning had reached its current level of specificity, before SpaceX existed, before Perseverance had drilled into the Martian surface and collected samples that might one day answer the deepest question in biology. And yet even Sagan, who believed passionately in space exploration, was trying to direct our attention back to Earth, to the preciousness and fragility of this world, to the importance of caring for the only confirmed home that life has ever had. This tension between the drive to expand outward and the responsibility to cherish and protect what we already have is one that I think the Mars conversation needs to hold more honestly than it sometimes does. Because here is the truth that sometimes gets lost in the excitement of rockets and timelines and mission architectures. Mars is not a backup plan. I want to say that clearly, because there is a version of the Mars narrative that frames the whole enterprise as a safety valve, a way to ensure human survival if something goes catastrophically wrong with Earth. Climate change, nuclear war, a sufficiently large asteroid impact. The argument goes that having a self-sustaining colony on Mars would ensure that humanity survives even if Earth became uninhabitable. There are two serious problems with this framing. The first is practical. Even the most optimistic visions of Martian settlement involve thousands of people on another world, perhaps tens of thousands over the course of decades. Earth has 8 billion people. A Mars colony for the foreseeable future is not a meaningful refuge for Earth's population. If something went catastrophically wrong with Earth on a civilizational scale, the small number of Martians in any realistic near-term settlement scenario would not be sufficient to preserve or rebuild human civilization in any meaningful sense. The best insurance against civilizational catastrophe is preventing civilizational catastrophe. On Earth, the second problem is philosophical. It can lead to a kind of moral hazard, a subconscious easing of responsibility for Earth, because we tell ourselves we have a plan B. We do not have a plan B. Not really. Not for the 8 billion people alive today, or the children who will be born tomorrow, or the ecosystems that sustain all of life on this planet. The irreplaceable biological richness of Earth, the coral reefs and rainforests and deep ocean communities, the extraordinary complexity of life built over 4 billion years, none of that can be packed into a rocket and transplanted to Mars. It exists here and here alone, and it is precious beyond any calculation. Going to Mars should inspire us to protect Earth, not distract us from that obligation. The perspective shift that comes from seeing Earth as one world among many, as a pale blue dot in the cosmic dark, should fill us with tenderness toward it, not detachment from it. That is what Sagan was trying to say, and I think he was right. So what is Mars for then, if not as a plan B? I think it is for several things, all of them genuine and important. It is for science, the knowledge that we will gain from sustained human presence on Mars, about the geology and history of the solar system, about the potential for life beyond Earth, about the behavior of planetary systems, is intrinsically valuable. Understanding the universe we live in is not a luxury or a distraction from human problems. It is one of the highest expressions of what makes us human. The curiosity that drives us to explore is the same curiosity that drives medicine and mathematics and philosophy and art. It cannot be divided neatly from the rest of human flourishing. It is for inspiration. The Apollo program produced a generation of scientists and engineers who were drawn into careers of discovery by the experience of watching human beings walk on the moon. Space exploration creates a kind of cultural energy, a sense that the possible is larger than we thought, that extraordinary things can be achieved through sustained collective effort, that the universe is not closed to us. That energy has downstream effects that are difficult to measure but real. The children watching the first Mars landing will carry something from that moment for the rest of their lives. It is for perspective. The overview effect, the transformation in consciousness that astronauts report when they see Earth from space, small and whole and heartbreakingly beautiful against the blackness, is a real psychological phenomenon documented and reported consistently across decades of spaceflight. We cannot send everyone to space to experience it directly, but we can share the images and the stories and the understanding that produce a version of it from Earth. Every photograph of our planet from space, every video taken from the surface of Mars looking up at a sky with two moons, these are gifts of perspective to the entire human species. And yes, it is for the long-term future. Not as a plan B, but as an aspiration, over timescales of centuries and millennia. Becoming a multiplanetary species does increase the long-term resilience of life in the cosmos. The universe is old and occasionally violent. Gamma-ray bursts, supernovae, asteroid impacts. Over long enough timescales, spreading life across multiple worlds is genuinely prudent. But this is a reason to work toward permanent settlement thoughtfully and sustainably, not a reason to treat Earth as expendable in the near term. Let me tell you about a moment in space history that I think captures something essential about all of this. On Christmas Eve, 1968, the crew of Apollo 8 became the first human beings to orbit the Moon. Frank Borman, James Lovell, and William Anders flew 10 lunar orbits and then headed home. And during one of those orbits, as their spacecraft came around the limb of the Moon, they saw something that no human eye had ever seen: Earth. Rising above the lunar horizon, a small, impossibly blue and white sphere, alive with atmosphere and ocean and cloud, hanging in the absolute blackness of space above a grey, barren, cratered world. Bill Anders took a photograph. You know it. Earthrise, taken on Christmas Eve, 1968. One of the most reproduced photographs in human history. The naturalist Galen Rowell called it the most influential environmental photograph ever taken, because something happened when people saw that image. Something shifted. The whole environmental movement of the 1970s drew partly on the emotional power of seeing Earth from space. Whole, fragile, alone. The first Earth Day was 1970, less than 2 years after Earthrise. The Clean Air Act and the Clean Water Act followed. The image of Earth as a single living system, visible, comprehensible, precious, changed how people thought about their relationship to it. That is what space exploration does at its best. It does not take us away from Earth. It shows us Earth in a way we could never see it from the inside. It gives us the perspective to love it more fiercely and protect it more seriously. When the first Mars astronauts look back and see Earth, not as a large disk filling the sky, as the Moon astronauts saw it, but as a bright star, a blue point of light indistinguishable from the other stars to the naked eye, what will that do to them? What will it do to the billions of people who watch the footage? I think it will be something new, something that has no precedent, a perspective shift of a magnitude we cannot fully predict, and I think it will matter in ways we cannot yet see. There is a concept in philosophy called the overview effect's deeper implication. The idea that the experience of seeing Earth from a distance does not just change how you feel about Earth, but how you understand the relationship between individual human beings and the larger story they are part of. From the surface of Mars, looking up at the night sky, an astronaut would see Earth as one of the brightest objects visible, outshining everything except perhaps the Sun, the Moon, and the moons of Mars, a brilliant blue-white point of light. On that point of light, everything in human history has occurred. Every war and every peace, every symphony and every poem, every love story and every tragedy, every discovery and every catastrophe, and the astronaut, standing on another world, breathing recycled air inside a suit, surrounded by a landscape that no living thing has ever touched, is, in some profound sense, the furthest expression of all of that history. The person who traveled the furthest from the point where everything that mattered to our species happened. And yet they are not separate from it. They carry it with them, in their memories, their values, their language, their science, their love for the people they left behind. The distance does not erase the connection. It transforms it. It reveals, perhaps more clearly than anything else could, how thin the thread is that connects us to our origin and how strong we are always, wherever we go, the children of Earth, of 4 billion years of life, of the particular blue sky and the particular smell of rain and the particular quality of morning light on a world that made us and that we are responsible for. Going to Mars does not change that. It deepens it. I have one more thing I want to say before we go into the final section of this video, the conclusion, the place where everything we have explored together lands in its final form. I want to say something directly to you. You watched this video. You stayed with it through 9 sections, through orbital mechanics and radiation physics and bone density, and 7 minutes of terror and terraforming ethics, and the pale blue dot, and the overview effect, and the meaning of 4 billion years of life preparing to cross interplanetary space for the first time. That is not a passive thing. That is curiosity in action. That is you choosing, out of all the things you could be doing with your time and attention, to ask a big question and sit with a complex answer, to follow an idea wherever it leads, even when it gets hard or uncomfortable or humbling. That curiosity, your curiosity, specifically, is part of the same thread. The same human drive that built the first telescope, that cracked the genetic code, that calculated the orbital mechanics that make Mars missions possible, that built the Perseverance rover and watched it descend through the Martian atmosphere on 7 minutes of terror and felt that wave of relief and joy when it landed safely. You are part of this story, not as a spectator, as a participant. Every curious mind that engages seriously with these questions is part of the culture that makes exploration possible. The scientists and engineers who will build the Mars mission grew up watching videos and reading books and asking questions that led them to careers of discovery. The chain of inspiration is real and traceable, and it includes you, so thank you for watching, for wondering, for caring about the answers. The universe is incomprehensibly vast. We are, by almost any measure, small and brief and fragile, but we are also the part of the universe that knows it is vast, the part that wonders, the part that builds telescopes and rockets, and asks questions that have no easy answers. That is not nothing. That is everything. Let's go back to the beginning, not the beginning of this video. Further back than that. Go back to a night, any night, sometime in the last 100,000 years. Somewhere on the African savannah, a small group of human beings is sitting around a fire. The flames push back the dark just enough to see each other's faces. Beyond the firelight, the night is vast and full of sound. Insects, wind, the distant call of something large moving through the grass, and one of them looks up. Above the smoke and the orange glow of the fire, the sky is filled with stars. More stars than most of us ever see today, because there are no city lights, no haze of civilization, just the raw, unfiltered night sky of a world that does not yet know it is being watched. One of those points of light is reddish, slightly different from the others. It does not twinkle the way stars do. It holds its color steadily, moving against the background of the fixed stars over the course of weeks and months in a pattern that a careful observer, watching night after night, begins to recognize. That person around the fire, your ancestor and mine, looked at that reddish point of light and did not know what it was, did not know it was a world, did not know it had mountains taller than anything on Earth, and a canyon that would stretch across an entire continent, and polar ice caps, and a thin butterscotch sky, and ancient riverbeds carved by water that flowed billions of years before our species existed. They just looked at it and wondered. That wondering, that impulse, so simple and so ancient, is where everything we have spent this video exploring began. The orbital mechanics and the radiation shielding and the nuclear propulsion and the 7 minutes of terror and the pale blue dot and the first Martian child, all of it traces back to that moment. A human being around a fire, looking up at a reddish light in the sky and feeling the pull of the unknown. We have been on our way to Mars for 100,000 years. We just didn't know it yet. So, let's answer the question. Completely, honestly, in its fullest form, how long would it really take to reach Mars? The short answer, the one that fits in a headline, is 6 to 9 months. That is the transit time for a spacecraft using current chemical propulsion on a Hohmann Transfer Orbit during an optimal launch window. It is the answer that applies to every successful Mars mission flown so far. It is the baseline, but you now know that the short answer is only the beginning. The medium answer, the one that accounts for near-term technological advances, is 3 to 4 months with nuclear thermal propulsion, or 6 to 13 weeks with nuclear electric propulsion. These are not science fiction. They are engineering programs in active development. The transit time to Mars is not fixed. It is a problem being solved in real time by real people, and the solutions are getting better. The long answer, the one that lives on the horizon of human possibility, is days to weeks. If fusion propulsion or other advanced concepts reach maturity over the coming decades, it is the answer that belongs to our grandchildren or their grandchildren, or perhaps to the first generation of Martian-born humans who build the technology their parents only dreamed of. And the complete answer, the one that tells the whole truth, is this: a round trip to Mars, under current technology and mission architecture, takes roughly 900 days, 2.5 years of transit, surface operations and returns and journey combined. It requires surviving 6 to 7 months of continuous radiation exposure each way, 500 days on a world that will kill you instantly without a suit, a return journey that rebuilds on top of everything the outbound journey cost you physically, and a readaptation to Earth's gravity that could take a year or more of intensive rehabilitation afterward. It requires leaving everyone you love behind, with up to 44 minutes of signal delay standing between you and any conversation with them. It requires confronting the psychological reality of seeing Earth shrink to a point of light, and then a dot, and then something your naked eye can no longer distinguish from a star. It requires in the most literal sense, giving a piece of yourself that you will never fully get back, and people will still go. They will go because the human capacity for courage in service of curiosity is one of the most extraordinary things the universe has produced in 4 billion years of biological experimentation. They will go because every generation has its horizon, and ours happens to be 40 to 400 million kilometers away. They will go because the questions waiting on the surface of Mars about life, about history, about what we are and where we came from, and whether we are alone, are questions worth crossing an ocean of space to answer. They will go because we are the species that goes. Now let me tell you what I think the most important thing you can take from this video is it is not the transit time, it is not the propulsion technology. It is not even the biology or the engineering or the philosophy. As important as all of those are, it is this: the universe is under no obligation to be understandable. It is under no obligation to produce creatures capable of asking questions about it, let alone answering them. The laws of physics could have been different. The constants of nature could have been tuned in ways that made stars impossible, or chemistry inert, or complexity unable to arise. Life could have remained impossible, or could have arisen and been extinguished before consciousness had a chance to emerge, but it didn't. Instead, we are here, on a small rocky planet around an ordinary star, equipped with brains capable of imagining other worlds and hands capable of building the machines to reach them, and hearts capable of feeling the weight of what it means to try. We are here, and we are looking outward, and we are going. The universe made something that wonders about it, and that wondering creature, fragile, brief, extraordinary, is now preparing to take its first step beyond the world that made it. I do not know a more beautiful fact than that. Tonight, if you can, go outside. Wait for your eyes to adjust to the dark. Look up, somewhere in that sky, its exact position depending on where Earth and Mars are in their orbits tonight. There is a reddish point of light. It might be bright and obvious, or it might be faint and easy to miss, but it is there. Look at it, really look. That point of light is a world. It has a surface area roughly equal to all the dry land on Earth. It has the tallest volcano in the solar system, Olympus Mons, rising 22 kilometers above the surrounding plains, and the longest canyon system, Valles Marineris, stretching nearly 4,000 kilometers across. It has dust devils and frost and ancient impact craters and layered sedimentary rock that records billions of years of planetary history. Right now, as you look at it, there are rovers on its surface. Perseverance is there, drilling into ancient rock and collecting samples that may one day answer this question of whether life ever existed beyond Earth. Ingenuity, the tiny helicopter that was only supposed to fly 5 times, has completed dozens of flights in an atmosphere so thin that engineering a working rotorcraft for it was considered nearly impossible. We are already there. In a real sense, we are already on Mars. Our machines are our advance guard, our scouts, our eyes and hands on the surface of another world, and in the years and decades ahead, we will follow them. When you look at that reddish point of light, you are looking at humanity's next destination, the next chapter of the 4 billion year story of life on Earth, the place where, for the first time in the history of this planet, a living creature will take a breath, carefully, inside a suit, on another world. You are alive at the moment when this becomes real, when the question shifts from could we to when, and then from when to soon. You are part of the generation that gets to watch this happen. That is an extraordinary thing to be. This has been the full answer to the question, how long would it really take to reach Mars? The physics answer is 7 months. The engineering answer is getting shorter every year. The biological answer is that the journey costs more than just time. The philosophical answer is that the cost is worth paying. And the human answer, the one that encompasses all the others, is that we have been traveling toward Mars since the first night someone looked up at that reddish light and wondered. We have been on our way for a very long time, and we are almost there. The cosmos is not finished with us yet, and we are not finished with it. And if Mars felt far, wait until you see what it actually takes to reach the nearest star. Click the video on your screen right now to explore how long it would really take to reach Proxima Centauri. We're talking distances that make this entire journey look like a walk around the block, and I promise it will break your brain in the best possible way.